that's it. It's all good. We have no experience in machine learning or fast AI. So, Gilad. Yeah. Yeah. Yep. I've been there a very, very long time. One of the OG reviewers. I think my number was like 216 or 219 or something like that. I think so. Yeah.
layers, right?
I have
But
no
then-
idea what ResNet 18 is, but that sounds right. I mean, it's a pre-trained model that you got from the
Right.
internet.
Yeah, yeah.
Someone else trained it. But
Correct.
then when you're doing fit on that, I don't know if it's wiping it and just using the architecture. That I don't know. It could be wiping out the weights and just using the architecture that you gave, or it could be continuing training on all the layers. Actually.
So I'm just gonna start off.
Yeah, fine tune in theory. The idea of fine tune is like you get someone else's model.
Hold on. I'm sorry. There was a slight technical issue with the sound. Well, so there's like this whole like I show you and all this like MIDI aggregate and stuff. But when I went to go change it back to the settings where it usually is, both of your voices just started like going on a loop. So it did sound like a pretty cool like EDM beat in my headphones, and I'm not sure if the people on the stream heard that at all, but that would be like the only thing they probably heard so far. And there it goes again. Hold on. It's like, I don't know why it keeps looping.
Well, why is that? Is it because we have an extra audio coming in? But Zoom should just do the same, right?
It shouldn't. Zoom should be the same. Could you talk again?
And now I'm
Oh boy.
Any ideas? Otherwise, we could just like not stream and record our audio. I mean, I could like switch on my recording.
Try it again.
Unless you think you can figure it out quickly. What?
It's not. I don't know if. Can you just like go on the stream and then listen to and see if you hear, like, just you guys continue the conversation, and then I'm just gonna try to make it not sound like a.
I can't multitask this much. I can look at the stream to see how it sounds. If you give me a second, I can check that. I can hear myself okay on the stream.
It doesn't sound like multiple, like you don't sound like an echo?
No.
Okay, so I'll just deal with it on my end.
That's no fun for you.
I mean, at least it's like it's not looping. Like
I don't think it's looping on the stream. Yeah.
Yeah.
Mm-hmm. So it's just you can't hear anything.
No, I could hear you guys, but it's like I hear you.
It's like you're hearing us a bunch of times.
Yeah, it's just like a monitoring issue, I think, on my side, but I don't know what I'm monitoring.
Maybe your mic or the Zoom mic. Who knows?
Who knows? Anyway, you guys continue. I'll figure it out.
Okay. Oh, hello. So, okay, so audio issues aside, where are we? Okay, so I just I just ran this couple of cells, which trains this small model. And I wanted to do this because I wanted to look into the docs for fine tune to see what's going on in there. Let's see. So it has this. I gotta get the. No, I just did that, huh? All right, I don't need that. Learn that fine tune. Okay. Fine tune with freeze for freeze epochs, with unfreeze from epochs using discriminative. So, does this tell you anything, Gilad?
Discriminative LR is discriminative learning rate, I think. But wait, go back to that.
Sure.
Fine tune with freeze for no. What happens if you click show in docs?
Yeah, I just opened it over there. So I just text it there. And then sometimes they have some helpful examples. But this one doesn't tell me much on the first look. So epochs, this is what we put in. It has a base learning rate defined, so you can change it too, like for the other ones. What, like freezing epochs, what would that mean?
I don't know.
What does it mean then?
That's like their jargon, basically. They have a lot
so
of
that's
their
not
own
like
jargon.
a channel.
No. This is not like a, well, it could be. I'm not really into deep learning. That's the thing.
Mm-hmm.
So it could be something that's been a big thing since, I studied deep learning 4 years ago, but I doubt it. I mean, freeze epochs just sounds like I don't get it actually. Why don't you Google that, freeze epochs?
It could be also actually that I'm going to do that. I'm just going to give it a try first. What happens if I already understand that the base learning rate, I can change it, but it just has a default of 0.002. And then it has a freeze epoch default of 1. So if I put in a 2 here, I'm just interested because it was doing 2 times 1 epoch. No, that's more likely here. If we change that one. All right, I'm gonna run this and then head over to Google and look what freeze epochs means. What's that all about? Nick always laughs at me when I put in a Google search because they're very conversational.
There it is. Can I explain what freeze and unfreeze?
Yeah.
They have decent forums, I think, right?
Yeah, they're really nice. There's a lot of info in there. Very active too. Freeze and unfreeze. Effectively allow you to decide which specific layers of your model you want to train at a given time. Turn off training for that layer. Which specific layers? I believe this is done because we also the early layers of our models are already going to be well trained to doing what they do, recognize the basic lines, patterns, gradients, etc. So you really think that this transfer learning essentially is just applied when we do this fine tune, and if we do fit, then it just does it all. Like calculating all the weights.
If you made me like pick an answer right now, yes, that's my best guess. I would be kind of surprised if fit meant something else. The thing is, there's 2 things you could do with fit. You could either continue to fit where you left off and it fits all the layers, so it continues to train all the layers, or that basically means it's applying back propagation to every single layer. But the weights aren't reset. That's the big question. Is if it's wiping the weights out, then it's going to be really, really bad results, because ResNet 18 was trained on ImageNet, I'm sure, and that takes weeks, or well, depending on your budget, it takes time. So. No, I mean, it's actually the fastest guys managed to train it in like an hour or something like that. They broke a record because they optimized such and such thing. So they've gotten it to go really fast. But It takes a while. Yeah.
Mm.
Yeah. So it won't be very good if you don't do the transfer layer. If you don't do the that's what makes deep learning so exciting actually, is because you can just out of the box use someone else's work.
Right.
But that was different though. So freeze and unfreeze is he even had a range, so you can actually say like you can use freeze to and int, so you can actually say how many layers you want to freeze.
Mm-hmm.
But what we were looking at is freeze epoch, which is different.
Was it called freeze epoch?
Yeah, it was called freeze epoch, and that was different. Right? Freeze
right.
epochs.
Yeah, it does. Yeah.
That's not freeze unfreeze. That's freeze epochs.
Fine tune with freeze or freeze epochs, then with unfreeze from epochs using discriminative learning rate. With freeze for freeze. Fine tune with freeze for freeze epochs.
It doesn't make any sense.
I'm also confused about this sentence. Yeah. With unfreeze from epochs.
And the thing is, epochs is the number of times you train, like the number of times you show the data set. So I don't understand what that has to do with the amount of layers that you're freezing or unfreezing. Well, I mean, actually, no. Okay, is the very first parameter epochs, that's like how long do I want to fine tune for? That's very normal. Like epochs, you pass that in. Like you pass in how many times you want to train for. That's a very normal deep learning thing to do. But the unfreeze, I mean, no.
It's also not really like where is this passed? It must be like some parent class of this or something. It's not really an input here.
Yeah.
You can give it some moms though.
Fine tuned with freeze. Yeah, I don't know. Was there anything else in that forum?
Yeah, let's see. Unfreeze all layers of your model, so you will be training later layers. Freeze will set all of your layer groups except the last one to be untrainable. Okay.
There's a different question I found where freeze epochs within the fine-tune function was asked in April. Nobody ever answered it though.
What did they say?
I don't understand it. The answer was nobody answered. So what they do say is, I understand that discriminative fine-tuning whereby different layers are provided different learning rates. So that's what discriminative learning rate would be. That's information.
So I would pass in, if I would do a discriminative learning rate, I would actually pass in like some sort of like a collection or what that gives like a learning rate for each of the different layers or what?
I guess so. Yeah, or maybe it's some kind of automated way of doing that. Like you give one number and it just divides it up automatically. Like, I don't know. All of these things are like this kind of stuff, this discriminative learning rate. It's all like what they're doing. It's all these techniques to get better results. Like, and I haven't studied that kind of stuff much. Basically, like I've spent most of my time thinking about what it all means, and less about how to do it well.
Yeah, I'm definitely at the what it all means stage.
This is like an engineering thing, like this is pretty cool, but like they figured out that if you do such and such thing, you'll get either better results or it'll go faster, or most likely both. Nick, are you still there?
Yeah, I just fixed the audio issues, so I'm back. And now I hear you guys only one time. And unfortunately, not like an EDM concert.
Congratulations.
So, yeah, we're back. Cool.
So I got some little change here that we can hop off on, which is I added this freeze epochs 2 here, but left the epoch number at 1. And this time when it did the training, it did 2 epochs for the first time and then 1 epoch for the second time. Before when we didn't have this in here, it just did a 0 epoch 2 times.
So what is this? What is freeze epochs do? That's,
We
I
don't
guess, like
know.
what we kind of were trying to figure out, right?
Yes. But what it does practically in terms of results here is it adds one line. Like it doesn't one extra epoch in the first time that this fine tune runs these two sets of epochs. So the interesting thing, Gilad, is that like usually it just puts them, if you don't do fine tune, if you just do a normal fit, right? Like you get the expected how many epochs you put in, right?
Yeah,
So 2,
yeah.
and then you get 1 line per epoch, and you get all this training loss, valid loss, error rate, and time. But this fine tune does 2 things. Usually you don't have these 2 headings with any other fitting.
Yeah.
Well, these also look like, if you go back to where it said like freeze and unfreeze, maybe it was in
you
like
mean the docs
other,
or what?
Yeah, in the docs. It said something about learning. Was it like learning groups or something? Like scroll a little bit up. Oh no, right there. Right? Fine tune freeze unfreeze epochs. No, maybe it was a little bit. I like glanced at the screen and then I saw something about.
I don't remember scrolling around a lot here, but maybe it was in the forum.
Maybe it was in the forums, yeah.
It's something in this?
Yeah, just I guess
or
like
up there with this guy.
Search for like group or something, like
group?
Find group. Yeah. So all these layer. Does that have anything to do with it? These like layer groups? Is that what what it looks like in the notebook now, where it's grouping the first and the second epoch, and then now it created another group with just one. And that's
epoch groups?
Yeah. Go back to your.
No, but that doesn't make any sense. This makes sense. What that forum posts with the groups. You're making groups of your layers and you're freezing, unfreezing them. But
if you think of the layers, then it makes sense, right? That's what I understand too, yeah, from what you were explaining.
I just don't get what a freeze epoch is.
Like, is this not 2 different groups right there? Like the first 2 and then the second one?
But so what Gilad was saying before is that like the freeze usually, like if you have like a transfer learning thing, it usually like it treats a lot of the model as already trained, and then just all of those layers up to a certain amount, and then usually you just train like the last one or the last few ones, and the rest stays as it was.
Okay.
And then like freezing, you could freeze as many layers of this original model as you wanted. Maybe you do, I don't know, resnet 18, you freeze 17 layers or something. I'm just talking out of my ass, but something like this.
No, that's about right.
So is this saying that it's fine tuning? So you're freezing the first 2 epochs, and then you're training it again to get that last one, and then it's just separating it that way? So if you did fine tune where it says 1, if you put like 3.
Okay, yeah, let's experiment a little. Still doesn't make much sense to me. So now I don't know what I. Okay, what? Pop quiz. What do you imagine is gonna happen?
Yeah, so I think on the second grouping, it's gonna have 3 rows. So it'll have like 3 epochs. Because right now, what this tells me, I mean, I also jumped in. You know what? Okay, give me a sec. I'm gonna upgrade Zoom.
Oh wait, it's your call,
it's
right?
because there's 3 of us.
Yeah. Give me a sec. It's fine.
Oh, interesting.
Yeah, once you get 3 people, it makes you pay.
Yeah, 40-minute time limit. Yeah, so what I think is going to happen now is there's going to be 3 rows in that second grouping, where
and the first
one will have 2. So you're freezing it at 2, and then you're going to like jump to train another 3 after the first 2.
Why would you want to do that?
Oh, I have no idea, but that's what I think is going to happen.
Okay. Well,
it could be like this.
Right.
I don't know. Okay.
All right, I'm gonna read a little more in this forum post.
No, he's right. No, I understood the sentence now. I finally, it parsed the documentation. Yeah,
this
it
one?
makes sense to me.
This one?
Yes. Okay, so it's going to first fine tune with freeze for the number of epochs that you told it to freeze for. And then it's going to continue to unfreeze for the number of epochs. Okay, so first it does, but that doesn't make any sense, but it's not really fine tuning in that case. It's just tuning. But so first it fine tunes with it frozen for the freeze epochs amount. So first you're doing your tuning, and then you're unfreezing everything, and you're continuing to train with epochs from the epochs, and it's all doing it with discriminative LR. So it's a two-step process where step one is first I keep it frozen, and I do the number of freeze epochs, and then when that's done, I do the unfrozen with the first epochs. It's weird, but that's what that is absolutely what it's doing. I know.
So this
why
relates.
I want to do that, I don't know.
So wait, so this
Yes,
relates
Nick is
to
right.
Yeah.
Nick is right. That's 2, and the next one will be 3.
And this, wait, just for myself to recap. So this freeze epochs is the amount of times that it runs with frozen epochs. Is that like
Yes,
with the model frozen?
Yes.
So and all of the model frozen essentially, or what?
Everything but one layer probably. Otherwise,
okay.
Otherwise, it's not doing anything.
And then we run 3 more epochs with everything unfrozen.
Yes.
Okay.
I don't know why you'd want to do that.
Probably
they must have a reason.
Figured out that works or does something useful, I guess.
So I guess the reason you'd want to do that is like, first you want to bring up this is just me spitballing, but like when you do transfer learning, you want to fine tune the last layers. So the idea is that the base layers have learned these kind of more general abstract things. First of all, let me preface this by saying I don't really believe anybody knows. I think there's just a lot of like experimental evidence and people trying stuff, and then these kind of like, this is my personal belief, and I haven't read a lot about it in the last 3.5 years, but I've anyways, poked around enough. So the kind of folk, what I consider to be like folk tale, like what I've heard a lot from blogs or whatever, is that the base layers learn these kind of very abstract things like lines, edges, and kind of more meta. And then the higher layers, the deeper layers, learn very specific things. And those specific things are specific to your task. And so if you take something that's been trained on ImageNet that is, what do you call it? It's been trained on ImageNet and with, 10 million images or whatever is there, then everything it learned from those general images can be helpful to your specific task, but you need to fine tune for the final task. That's the idea. So maybe that final layer is you want to get that up to speed first, like you want to just train that specifically to get it kind of close in the ballpark, and then you kind of want to smooth everything over. I'm thinking like a pottery thing, like I start off by focusing on the top layer, and then I kind of want to smooth the whole thing out, if that makes any sense. That's why I train on all the layers. I don't know.
It sounds nice.
Oh.
There we are.
It must be something they wanted to do enough times that they decided to build a function for it.
Well, one thing that I'm definitely going to note here is that, what am I going to note here? Definitely, I don't know, I forgot. Fine tune. So this is one thing that I want to remember. Fine tune, related to transfer learning, probably. That makes already some sense then. And then freeze epochs. Is how many epochs to run with a frozen model, and then I don't know, is it just called epochs? I think it's just called epochs.
Yeah, we still don't really know how many layers are being frozen or unfrozen.
So I do think it's just the first 2 layers, right? You're running them and then freezing them. So I would guess that this is the same thing as running. You would get similar results if you're just running 5 layers, right? Or like five epochs. Like the training loss, the error rates, all that stuff would look very similar, because I think you're just jumping from that second epoch. and just
The
continue
weights
training.
are not being reset. You are continuing training, but the difference is after the first two, you've opened up all the layers. So now you're actually updating the weights all the way back to the of the entire model. So it's sort of like I'm trying to think of an analogy.
So I guess like I don't know if this may answer my question or not, but like it seems that this fine tune function, like right now we're not really using it to its full potential, but we could be doing it in a way where it freezes the first two layers and then does this second grouping with some sort of learning rate or whatever other parameters we want to throw into it. And then we could also, from the locked initial layers, create another grouping with different parameters and then kind of compare. So like this group wouldn't influence another group. That's what it kind of sounds like to me, that we're not really using this fine-tune function to its like full potential.
I don't think we're deciding for layers, amounts of layers with this. Or like with anything here. I don't think our input decides how many layers of the model get frozen. I have the feeling this is more implicit somewhere in there, somewhere deeper.
I think I would agree with Martin. If you haven't read about it already somewhere, he doesn't explain it. But I'm trying to parse what you were trying to say, Nick, or what you said. Sorry, I'm not sure I would agree with that, or I don't think that's what I think. I don't think that's my understanding.
I just don't think the easier way for me to understand this freezing thing is that it's related to layers, right? That's what we were talking about at the beginning. That you decide for a certain amount of layers of your model, you have this stack of stuff, and you say like this pancake stack goes into the freezer, and we're not changing anything there. But it feels like this is doing something else. Like it's not actually operating on the layers. How many layers stay frozen and how many of them get unfrozen is just implicit with the function, I think. And then this just means like how many epochs do you run on the frozen model and how many epochs do you run on the unfrozen model, I think.
Yeah, where the unfrozen model includes the original two that you were fine-tuning on, or whatever it was. We don't know.
Yeah, I don't. Does that make sense? Nick, what do you think?
I don't know. I think I probably just have to like look into this more.
So you can check the layers trainable attribute to know which layers in your model are frozen. Although this was a question asked in 2000
on the learner.
Yeah, who knows if this is still true though, because they've changed their API so much in the last 2 years.
Yeah, they did. It's a new model. Yeah, they did a big change recently.
I know. But yeah, the question is there an easy way to check?
How did you say it's called?
Well, the layer's trainable attribute. So there's a trainable train. Is there a layer? I don't know. Trainable.
Train evil.
Able. But
no.
No. Maybe it's on the
training.
All learners have a model attribute. Is there a model attribute?
Yeah.
And that has
layers? No. Training. All right, let's see if we can get something useful from that.
I can share you. Should I send you this? Just Google how to tell which layers are frozen. You'll see the fast AI post I found. But it's from 18. I'm not really sure.
That's the one you're looking at?
Yeah, exactly.
Part 2, 2018. learner.freeze to 0. Unfreezes all the layers, and learner freeze to -1. Unfreezes all the layers except for the last. Which layers are frozen? The layers' trainable attribute. Model.layers. April 18. Is there anything new? So this, maybe it looks like this is on a model object, not on a that would be, so I think there would be, let me see.
There's also a really good post I just found, when to freeze and unfreeze, which answers a bunch of the questions we were also discussing. And it is right what I was so basically yeah, that one. So actually, yeah, this ties into what we were just discussing pretty well. Yeah, so he's like, I don't get it. This is what I was saying, like I'm making up why we would do this. But the real answer though is we use a pre-trained model for efficient training, right? On this guy, this regular fellow.
This guy?
Yeah, his answer is really good. So we use a pre-trained model for efficient training. FastAI doesn't exactly use the architecture that was designed originally for ImageNet, but removes the last layer. So they pop off the last layer and then they append 2 fully connected layers. And the second one has as many output neurons as your number of categories. So the 2 layers that are appended are completely untrained. So they have completely random uninitialized weights. So we are doing this freeze training to bring those 2 layers up to speed, essentially, to get them kind of in the ballpark.
So you're saying like that's still the freeze training, that those 2 layers get attached.
Those
like
2 layers get attached. They are initialized with, so when you initialize your weights, they're initialized somewhat randomly, but close to 0 normally, or there's lots of different there's a whole science behind that, but it's random essentially. Like we just have no idea, just whatever. That's what we're going to optimize now. And then you need to train those 2 layers up. So that's what the freeze epoch is. That's training up those 2 layers. And it defaults to 1.
Are you saying that, so are you saying that like this 2, actually like this number says how many layers we're adding? No. Okay.
The two layers
it's always
are just
2
default.
Layers.
Yeah,
that's
it's always
just
2 layers.
Gotcha.
Well,
okay.
That's what I understood from that guy's post. Yeah, it's always 2 layers. That's just how FastAI does transfer learning. When you do learn equals CNN, learner DLS resnet 34, under the hood, FastAI has taken resnet 34, pops off its last layer. It appends 2 fully connected layers, where the second one is specific to whatever you want to do, essentially. So,
and the first one is going to be the new result of training the frozen resnet before, or what, so that to pipe it over to the last one, to the new
basically. One. Yeah, basically. And I'm sure that you don't have to have 2. You could probably just add another one, but they probably found that they got better results by doing it this way. So yeah, but that's exactly right. There are 2, you add 2 of them. The last one is the specific number of categories you're interested in, classifying for, and then that second to last one is essentially a connector piece. And then you're training up the weights. When you're doing freeze epochs, you're training the weights of those last 2 layers only. So you'll do forward pass, backward pass, forward pass, backward pass, do all your optimization steps, and you're just updating those 2 layers. That's for the number of epochs that you pass to freeze epochs.
Okay.
Then it automatically unfreezes the entire network and trains for the number of epochs that you told it to train for.
Nice.
Yeah.
Nice. Okay. I kind of get it.
Yeah, I get it.
I kind of get it.
Well, I don't think I'd be able to like repeat it the way so eloquently as Gilad, but I think
it's around with the frozen one.
Clears it up for sure.
Trains just on the to fault. Okay, and then epochs trains on the whole model, like all layers, right?
I'm sure you can customize that, but I don't think it's, I'm sure you can pass something somewhere to customize that. Everything is customizable, but that's the defaults.
Cool. All right. That's I'm happy with that so far. Like, I mean, that's the I feel like I got out of this that amount of understanding I wanted to. But that's just because I have the power of scrolling. I don't want to move on if there's like someone else wants, I'm just like going around.
No. I feel good. I feel the same way.
Cool.
I feel like a puzzle was unsolved. It was solved, not unsolved.
Unsolved.
So just so I'm on the same page, scroll up a little bit, Martin. So what's happening here is for the first two like freeze epochs, you're fine tuning essentially resnet 34 for the last two layers for two epochs, unfreezing it and then opening it up for the rest to train on.
Yeah, and the thing I would add is that last two layers are like brand new. They're new. You put them there when you started this thing. They didn't come from resnet.
Right. Okay.
So they actually just have they only have our. It's as if we had made a new model.
Yeah.
Right. It's like essentially freeze epochs. This deals with stuff without transfer learning, and then this epoch number adds in the resnet. Or did I mess it up again?
If you think of it as a house, so you have it like a skyscraper, or let's just say like a 10-story house. Like the freeze epochs is like when you built your model, you like knocked off the top, the roof, and like the top floor, and now you're building the new ones. That's what freeze epochs is doing. It's like building that top floor and the roof, and then you're fine tuned. Then once that's done, then you're kind of like, I don't know, painting the whole house or something, whatever. But it's the last two layers; they're brand new, so you're bringing them up to speed.
Mm-hmm. But wait, so the input comes from, like, we're bringing them up to speed in connection with resnet.
Absolutely.
No, yeah, okay, yeah. Not just on the data that we actually supply, which is really small.
No.
Yeah, okay.
Because it all filters through resnet. So the forward, every time you're up, so how does a network learn? That's the big question. How does a network update its weights? Can you explain that to me?
Nick?
I was going to say, Martin, you seem like you're more qualified to answer this one.
Why? Why would I be done as much about this as you have?
The power of scroll is literally
the power of scroll.
Well, this is the golden question. There's two important things I always like to look. When I try to teach this, there's two important things. One is, what does a network learn? And I think you guys, what does a network actually learn? What does it learn? What is the product of a neural network? What does it actually give you when you're done with it? And then the other is, how does it learn that? Those are the two questions. If you understand that, everything else is just window dressing.
Nice way to say. So I'm looking for, there's a nice graphic somewhere in here, somewhere in the depth of all these notebooks, but I'm probably not going to find it quickly enough. But let me try. Let me give it a shot. So what does it learn and how does it learn? So how does it learn is it passes, it calculates how wrong it is, essentially, or it calculates according to a specific metric, which is often how wrong is it in relation to some labeled data that you're passing it in, right?
Yeah.
And then collects all of these numbers, that represent some sort of difference to the thing that it should have actually been.
Yeah.
It collects that, then calculates everything, that's the loss somewhere in there.
That is the loss. You're describing the loss.
Right. Yeah, that's the loss, and it uses this values of the loss to try to like compare again to the loss. So then it calculates stuff again, like it does something else, changes the weights.
Wait, that didn't make sense what you just said.
Okay, so let me try. So we, to the loss, I get to the loss. I get so I start off with a couple of random weights. I throw this in. I do some cooking with it. I get some results that have a certain error, like they're wrong to a certain degree. That's my loss.
So you get some results. You get some results, and
Yeah.
then you compare them to some values that you take to be the truth.
Right. That's my labeled data, and
Exactly.
and I compare.
And
Is
then
that actually how wrong am I?
That comparison is using what's called a loss function. That's a mathematical function. So that's all right, and that gives you a number. That number is the loss.
Right, and then this is where this where back propagation comes in. From
Exactly.
what I don't all the way understand it, but I know that this is when it happens, which is like throwing the loss back into calculating the weights, right? Like I'm updating
so
the
what
weights.
it is so what it is the loss function is differentiable. That's one important thing. You have to just like memorize that. The loss function is differentiable, which is what allows back propagation to work. Which is so for gradient descent, forget about back propagation. For gradient descent to work, it can only work if you can take the gradient, and the gradient means it's differential. It's a gradient is a vector of
like how
slopes.
What's the slope at this specific point?
It's a vector of slopes. Yeah, it's a vector of partial derivatives. That's the word I was looking for. It's a vector of partial derivatives. So it's a stack of partial in n dimensions or whatever. So basically, if you just call it calculus magic, for the whole thing to work, the loss function must be differentiable. And then what gradient descent does is it assigns essentially blame to the inputs. So it says, hey, you weight number 1, you made me wrong by this much. Hey, weight number 2, you made me wrong by that much. Hey, weight number 3, you made me wrong by this much. And then because it knows that, you can actually just automatically update the weights to make everything a little less wrong. And that's that learning rate. So you multiply everything by the learning rate to take these steps. Now, backpropagation is just that idea of assigning the blame, but instead of just doing it on one set of weights, you pass it back through the network. So it's just gradient descent with the chain rule. So it's using the chain rule from calculus to pass that blame backwards through the network. So each weight in the network is updated by a proportion of its contribution to the rightness or wrongness of the output. So like so that's the cool thing, is it's very like micro targeted, right? So every weight is updated according to its contribution to that prediction. Or another way of thinking about it is its contribution towards that loss.
So actually what I was thinking with this updates is that the learning rate, which is one number from how I understand it, it gets applied essentially to all the weights. But what you're just saying now is that there's
it does.
Okay.
But each weight is well, no, the learning rate does, but it still gets now my math is failing me. It's been a while since I did it. Actually, I failed the backpropagation thing on my quiz that I had for my AI class. They made me do forward and back by hand, and I just got a 0 on that for the midterm. I was so pissed because like I should know how to do this, and I just could not figure it out. So no, it is a single number, but the weights they don't get updated. Oh wait, hold on, let me think about it for a second. If you're just doing it with a bunch of weights, then yeah, it's just a straight up update. They all get the same update because you're aggregating all those things. But backprop definitely adjusts. It's a localized thing. So I'm not sure.
I think there was, I have the feeling I even read something about that. It happens also that like some of the weights are actually going to have a worse performance the next time because the update goes like sweeps across all of them essentially, but it's going to be overall a lower loss. But it can happen that one of the weights might have been better in the previous iteration, just Yeah, so they can jump like maybe this one was
No,
perfect
that
actually.
makes
and
that
then-
makes sense, but I feel like the layers don't get all the same updates because of backpropagation, because of the chain rule. Maybe the weights
Okay.
in a layer get swept like that, but I feel like layer by layer they should be different update. Like each layer should get a different update than the other layer. Otherwise,
Okay.
what's the point of backprop if you're just updating all the weights by the exact same amount? That doesn't make any sense.
Mhm.
The whole point of backprop is that you're using the chain rule, which you'd have to look it up because I don't know it off the top of my head. But you're
Chain rule.
definitely it's the
Chain
chain rule
rule.
for
Backpropagation.
yeah, you can just write that. I mean, it's not. It's for,
For
calculus,
calculus, yeah.
but it's for partial derivatives in calculus. So it's like if you have functions that are it's functions of functions of functions is what it comes down to. But there's enough people who have tried to learn backpropagation, so they're all going to know. You'll find Google hits for chain rule for backprop also,
Mhm.
because it's been written about ad nauseum now for everybody
Mhm.
trying to study deep learning.
Is that a video or is that going to be because it's that article?
I don't know. How to find the derivative of a composite function. So it's if you have a function within a function. No, so this is fine one. The Wikipedia
This one?
is fine. Yeah, the Wikipedia one.
Wikipedia one. All right.
This one's loaded.
Yeah, yeah.
Okay. Well,
Hit it.
Yeah. So it's just f of g. It's the chain rule. Yeah. So it's f prime of x. You want to zoom on that? Yeah. So you have f prime of x. So you're trying to, but f is a composite function. So
here, that's where you're looking at, right? Am I right?
yeah, both of them. But the circle, what's the circle mean? It's the derivative of their composite. So basically, it solves the problem. What happens if f of x has within it another function, which is g of x? How do I take the derivative of that? Because
Okay.
f of x depends on another function. So it's a function. I want the derivative of a certain function, but that function itself, its input is another function. So it's how do we solve the math of taking a derivative where you have functions within functions within functions? And a neural network is exactly that. The last layer is this function which is depending on all the functions before, because every
Right.
layer is just a function. That's the important thing to realize about a neural network. Every layer is just an f of x. That's all it is. It's just an f of x. And it has an input and it puts an output. And then it passes to the next layer. So its output is the input to the next layer. So they're all, this is one giant composite function. So this chain rule for this that we're looking at, this calculus, this is what they do to assign the weights correctly. Because that's the point of using the gradient is so you know, so you can calculate the update. So yeah, the update must be calculated by layer. That must be right. It must be calculated by layer. And then all the weights of that layer get the same update. That makes more sense to me.
And then for the next layer, you have a different calculation, and it gets updated in a different way.
Exactly. Yeah, because you're taking the partials. You're taking the partial of the layer of the function that it depends on. So
What's a partial?
The gradient. The gradient.
Okay.
I'm probably using the word wrong, so I don't know. My math is pretty bad.
I wouldn't know. So
yeah, well,
I just don't know.
someone listening may one day know and laugh at me. But yeah, the gradient, for me, they're all kind of the same. Like, so this dz, dy, dx, those are partial derivatives. Each one of those is a partial derivative. It's a derivative with respect to something. So you have a partial derivative is when you have more than one variable. And so it's multivariable. So you have like three variables. So we can do derivatives in 2 dimensions pretty easily, like when you have an x and a y, that's pretty easy to take. You can just take the derivative of that. That's the slope. But if you have 3 variables, then you can't take the derivative of. You have to freeze one variable and like kind of slice it, and then you take the derivative with one of them, and then you just keep doing that. That's what a partial. I don't know. I never really.
Is that the slicing here? The notation looks like slicing. Yeah, it's like a.
Looks like that, but I don't think it actually is. I studied this really briefly enough to get an intuition for what it is, and then I stopped studying it.
Yeah, for me, I have a somewhat it's not really a goal in life, but I have like this thing that if one day I can look at a article on Wikipedia that is about math, and I can actually read it and understand what it's about, it's gonna be like a big explosion in my head, I think, because usually when I go to a math article, I'm just like blanking and all of the formulas everywhere.
Yeah. Yeah, I mean, when I started studying machine learning, I didn't even know what the sigma function, that the sigma for sum, the big, I didn't know what that was. That scared me. And then now I look at that and it's just like so obvious. So
yeah,
it
that's
just takes
cool.
time.
Yeah.
It just takes time. But I don't know calculus very well. And to be honest, you don't really need to. You just need to know the intuition of it. So, but I think after this discussion, I would agree with what you said, that probably every layer, I would put money on that. Every layer is getting the same update, all of them, but layer by layer it's different, because each one you're taking the gradient of thing to calculate that update.
And you're kind of like, I mean, that's my intuition now, is essentially like you're taking this derivative of a multi-dimensional curve, if you want to call it a curve, that includes all of the weights. Like there are all these dimensions, these weights, and then somehow there's like something that's equivalent, like a derivative that's equivalent to when I have two. No,
the weights are what make up the curve. So the weights are like it. No, that's right. But like if you just think in 2 dimensions, like if you just look at a parabola, y equals x squared.
Yeah.
So the weight is 1x squared. So it's the weight is the x actually. No, sorry, the x is the given. That's the part we don't know. So it's y equals mx plus c is the normal way I teach it. So mx plus c is a thing for a line, right? Y is the label. That's what we're trying to predict. Then mx plus c. X is the training point. It's the data that's given to us. And then the m and the c are the 2 variables that we can play with to find the line that best fits that data. So we're given a bunch of x's, and then we have to try to find the line that best fits that data. That's the basic idea. If you're just looking in 2D, that's actually like the easier way to start thinking about this. You try to fit just a line to a bunch of points.
And M would be the weight. And M would be the weights, and B, right, and B would be the bias, right?
Yeah, the bias.
Yeah, they actually had that in one of the other like the previous lessons, and they applied it to like the weights and the parameters. So that same
here.
I don't remember, somewhere, but they took that like y equals mx plus b, and then they changed. It was like m. They changed that to weights, and b. They changed. I think they just defined it to like bias.
It's probably in some. It's not really finding anything here. But who knows how these notebooks are organized.
I remember reading it in one of like the previous lessons.
Yeah, a bit hard to find, I guess, if it doesn't show up with a search.
I think I got dropped. What were you guys saying?
No, it was just one of the previous...
Nick was just saying that we had this...
There's so much of a delay.
Go ahead. I guess we have some lag. Yeah. We're talking over each other.
Yeah, in one of the previous lessons, they just laid it out as the same like function, like y equals mx plus b, but then replaced m to be, it was y is equal to wx plus b, and then b actually stood for bias, and then it wasn't m anymore, it was w, and w stood for weight. So like the same exact formula, but like put some like make it more semantic, I guess.
Yes, that's completely right. That's 100% right. Yeah. But the point is though, so now when you ask that question, the reason we started talking about this is when you ask that question, so wait, the original, when we were talking about the house example, we said, you said, well, the other levels of the house are contributing to that fine tuning, right? So in a forward pass, yes, because you're making this prediction. And so that prediction is based on all this matrix multiplication that's taking place, plus the activation function and stuff. But like each layer is essentially a matrix multiplication that produces an output. And then that output is the input to the next layer. And each layer is a function. That's the way I like to think about it. Every layer is a function, or every layer it's both a function and a matrix. A matrix is the function because it's just a bunch of weights. And when you do matrix multiplication, you are just producing a prediction from your function. That's all it is. But just in bulk, basically. Matrix multiplication is actually producing like, that's the cool thing. So that changes the discussion a lot. But matrix multiplication allows you to, put in 50 inputs and get 50 outputs all at the same time. That's what these batches are that we're passing through. So if you just pass one, it's not matrix multiplication, it's matrix vector multiplication. But it's still that vector, you have one vector, that's your input. You multiply that with matrix, that gives you an output. And then that output's a vector, and then you keep doing it until you play with the numbers so you get the kind of shape that you want for the output at the end. But the point is that it is just a bunch of functions that are stacked together. Each layer is a function. It gives an output. That output is passed to the next function as an input, and then that makes an output. And so they're all passing forward. And then at the top of the house, you've got these kind of fresh layers, which are like, they've never been trained, but they're still just going to make some prediction. And then from the back prop, it updates those two layers because it wants to update them, but the other ones don't get updated. Not until the first epoch is done. And then you unfreeze everything and everything kind of gels together. I guess.
Party.
But every time the forward pass happens, it's making a prediction, right? Each layer is making its prediction and passing to the next layer, which is then taking it as input and passing it as output. So they all are part of the prediction, and therefore they're all part of the process. They're not just being ignored. Like you're not just training two layers without anything.
Right. Yeah.
Because it's filtering through those first layers.
Yeah, it's nice to kind of imagine it visually, or like stuff dripping through. I'm actually more going because you have this house example where you stack on top. I guess in my mind it's more like it's turned around and you have like things like maybe layers of earth or something where like water keeps filtering through and dripping down. That's kind of how it goes in my head, but it's the same story.
Yeah.
All right.
Oh, so wait, what's learned by neural network? Let's just finish that. It's worth remembering this too. What does it learn when it's done? What is actually learned, and what does a neural network learn, or a deep learning thing learn? What does it actually learn?
Okay, let's see. I guess it learns what is the number. I mean, I guess it learns it learns what set of weights produce the lowest number, the lowest loss.
That's exactly right. Yeah. That's it. It's just these weights. That's crazy to me. Like you'll people like this GPT-3. You guys heard about that?
Mm-hmm. Like the language modeling.
Yeah, they spent like literally millions of dollars training that thing, and it's just a bunch of numbers. Like that's all it is. Like you could send it across like like a 30 megabyte file, I'm sure. Like it's just the numbers that it learned for these weights. That's all it is. And when it's done, it's just like the magic numbers for a recipe for a function. It's totally crazy.
Yeah. Yeah, it's interesting. Like there's like something in this course also where he talks about exactly that at the beginning, where it's like, okay, so you need some GPU to you need some hardware. Maybe you don't even need a GPU, but you need some good hardware to train it. But with transfer learning, right, you don't even need that good of a GPU set or whatever. But essentially, once you have your trained model, you have this program that you can run on anything, more or less. Like you can run it on a CPU easily because it doesn't require much.
Because actually it's the cost of doing all those forward and backward passes. It's just doing a ton of matrix multiplications, but when it comes to actually using it, it's not that expensive, depending on what you want to do with it.
Yeah. Cool. I'm scrolling forward. fine tune. Okay. Yeah.
So now we know what that one is. That one is
Yeah,
automatic one for epoch. So but it does automatically do the freeze first. That's why you have two outputs. So the first one is the.
And does it do
defaults.
some freezes? Like how much does it freeze? Okay, it freezes one. Yeah. Okay, I see.
Yeah.
It does that automatically. Yeah. And then it's interesting that like for this, because this is the first project that he introduces, right? This cat dog classifier, and then with this, like with using resnet and with using this transfer learning, he actually just trained for one epoch after everything is unfrozen, and it gives you like really good results. It's like, it's fun to see this in action.
Yeah.
All right, so
in normal machine learning, one epoch is the standard, just so you know. This idea of passing the data set like 100 times or whatever is only in deep learning to do that. Like in normal machine learning, when you just train something, you just fit it once. You would never fit it over and over and over and over again.
Oh, interesting. That's just a deep learning thing. That's interesting.
The epochs is just a deep learning thing. Yeah. No, I mean it works fine, and it works well, and it's the strategy it works well. But like, yeah, if you make a decision tree or you do a k nearest neighbors or a lot of other algorithms, you don't have this idea of epochs. You just train the network. You just train your model once.
Because you don't update stuff. You essentially pass one set of weights, right? Like you figure out what's one set of good weights. I mean, weights is not the right term probably in that case.
It's whatever it's learning though. It learns whatever it's learning once, and that's that.
Yeah. Okay. So, anything, Nick? Do you want to add anything? Did you have any?
No, just so like for that last thing, is that because you're like including transfer learning into like machine learning, that you only do this one epoch? That you're not starting from scratch, you're getting it from some sort of there's a base that you're building off of?
Yeah, I think so. That's my understanding.
Yeah.
Otherwise you couldn't do it.
With the one epoch, why it works so well with one epoch?
Yeah.
Or just like what's the reason behind the one epoch? Is it because it's using, or it's like leveraging like transfer learning because you've already, like you have this model that's already trained, and then you're just kind of training it just for your specific use case at one time?
Yeah.
Yeah?
Yeah.
Okay.
Yeah.
So behind these like machine learning models, it's always this deep learning to get that model. And then when you use it for machine learning, you just train it for your own use case once.
I think we're mixing up the terms a little bit.
Yeah, I don't think.
I mean, for me, so machine learning is the field of machine learning is the field of machines. It's like literally that stupid. That's my definition. It's like
it was actually breaking up really bad. I don't know if it's just for me. Nick, did you hear Gilad normally?
Yeah, I think you said machine learning is like the field of just machines learning stuff, like super.
Okay, basic. Good. Then it's just breaking up for me. Okay.
Yeah.
Sorry.
Well, it looked like he was struggling to hear me too, though. Maybe I'd switch the internet too. Hold on. I'm going to drop and join back.
Bye.
Bye. Yeah, I kind of pieced what he was saying together with like.
But it was also breaking up.
Yeah. I was like, okay. Context blips.
Good parsing there.
Yeah. But this is nice because like last time we were here, we were kind of scratching our heads with like, what does this fit function do and how is it different and why is it grouping these like. Why is it creating a brand new table when it was doing fine tune versus fit, but the rates looked exactly the same or very similar? Now we know what it's doing with like the freezing and training just that last layer and everything. So that was kind of nice.
And I think the results were always better with fine tuning, right? Was that's a fine-tuned one, the Fs?
I don't know.
Okay. Is it more
Hard to
clear
say.
now?
Hi.
Welcome back.
Hi. Is my voice more clear?
Yeah.
I mean, it was clear before. It started to break off when you were talking.
So
Jumpy.
basically, Nick, machine learning is the field where machines learn, and that's like anything. Anytime a machine is learning something, you can call it machine learning. So deep learning is just a subset of machine learning. Deep learning is a certain algorithm. It's this neural network thing, and it's honestly, it was just like marketed really well by somebody at some point to be made sound like it was something else, but it's really just like a kind of machine learning. It's a machine learning algorithm. There's many different ones. So, but I think your intuition about what you were saying is right. Like if you want to just have a model that does something for you, if you want to just make a classifier or like a product thing, then you fine train, essentially. That fine tune, that is like the way to go, for sure. And that's not just for images, that's for languages, that's for lots of things. And there's lots of great, there's a website called Hugging Face. They're a company and they do all the language models, and you can just go and get a language model and start using it and fine tune it for your needs by giving it the documents that you're interested in learning about, and then you can kind of leverage that essentially the work someone else has done, which is why deep learning is so popular, because it works so well.
Mm-hmm.
Yeah, Hugging Face. Yeah, they're a pretty cool company, I think. Although I think they got bought recently by somebody, so we're always a little worried when that happens.
We don't know anymore.
Well, you just never really know, right? But my friends all use them, and I've heard lots of good things about them.
Mm-hmm.
Actually, I'm pretty sure the guy who wrote this book with Jeremy Howard works for them. Sylvain.
I think that's his name.
Sylvain. I never read it carefully. Yeah, I think he works for them. I'm pretty sure he works for them. So yeah, I think your intuition is what you were saying, is that you can essentially get a model, use it for your purposes, and because you're only interested in that kind of fine tuning it, specifying it for your use case, it only takes one epoch. And that's true. But I imagine there might be times when you would want to run more than one epoch.
Right.
It all depends on like how well it's running. You want to get the best performance you can get.
Yeah, I think like one point maybe like, so what I think, because my understanding was that Nick was referring to what you said before about other machine learning stuff where you usually just like, there's not really the notion of an epoch, but you just fit once.
Yeah, those are just different algorithms.
That's just different algorithms, yeah. And for this one,
they
you would like even,
yeah.
right? Even if you do transfer learning, like doesn't matter whether you do transfer learning or not, you're doing deep learning in these cases. And this usually comes just with running multiple epochs, or at least with this concept. And then there's an edge case of you do transfer learning, you just need one, and it's fine.
Yeah, exactly.
Possible. Yeah.
Exactly. Gotcha.
That sounds right. Yeah. And the epochs thing is with gradient descent. It's because you can optimize, and you're taking these steps, and so the steps aren't maybe big enough, so you just keep doing it for a longer amount of time. And it's just essentially okay to show the data over and over again. But in other algorithms where they're learning in a very different way, essentially, it just doesn't really work.
Cool.
It's just like,
makes sense to me.
It's like a different different world, basically.
Yeah.
Gradient descent is just like one very specific kind of learning, and other like decision trees, for example, are just very different the way they even work.
What's your favorite machine learning algorithm, Gilad?
Yeah, probably gradient descent. I love it. Decision trees and gradient descent. These are the two most popular at this point. I mean, the thing is,
you just go with the most popular ones, huh?
Well, I mean, I teach this stuff more than I do it these days, but like, yeah, pretty much whatever's working well is what I would try to use, So neural networks are really popular right now, and they're really good. And deep learning is also, gradient boosted trees, which never really studied, but it's a kind of decision trees plus gradient descent, like merged into some kind of hybrid monster, is supposed to be really good too. So yeah, if I had to win like competition or if I was making a product, those are the two things I would try first. Let's say it like that.
Mm-hmm.
But there's all kinds of yeah, I mean whatever. Let's keep
I think
going.
I like
Yeah.
K nearest neighbors.
Yeah,
Because it
that's
sounds
funny. I was
nice.
just thinking about that. I almost said that out loud. I was like, well, K nearest neighbors is also really interesting for some other
Yeah.
reasons, but I didn't say it.
I kind of like that
Yeah.
one. I mean, I only did like a very intro machine learning course also like a couple of years ago, but
the
I
thing
found
is,
that one fun.
you can combine
Right.
K nearest neighbors with deep learning. There's even
Yeah.
K nearest neighbors deep learning. So instead of using gradient descent, they
sure
use
there
K nearest
is.
neighbors to
Oh.
optimize it. So
Oh, that's interesting.
yeah, see, so the idea is the deep learning, actually you can divorce the learning algorithm. The optimization algorithm is separate from the hypothesis function. So the hypothesis function is the topology of the network. That is all the different matrix multiplications, you know, that make the output, right? Like the actual network that all the water flows through. And now then there's the optimization algorithm that you apply to that network to find those best weights. So gradient descent is by far the most popular, but it is not the only one. So there's been a lot of work done to try to find other optimization algorithms that can find the weights better. And there's even some work being done to see like there's a recent paper of like a year ago where they found that using random weights, they could actually get really good results as long as they had the right topology. And so that they're hypothesizing that a lot of the learning power of a neural network comes just from the topology and not even from the weights themselves. So
topology meaning which way do you set up the layers? Is that what it is?
Yeah, the width, the layers, how they're connected, what activation functions you're using or not using, all that kind of stuff. So the structure of the network, essentially, the math of the forward pass. You could think of it like that. The weights have nothing to do with it. It's just like the way you set up the forward pass is all that matters.
Interesting.
And they were actually able to train like a race car to a game race car to drive in circles with completely random weights just by having the right network topology.
Wow.
So I can find the link for that blog post, or it was a paper. It came out like a year ago. So there's all kinds of different ways to optimize these weights, and gradient descent and backpropagation is far and away the most popular, but it's not necessarily going to be the one people will be using like 20 years from now.
Right.
So it's an area of research for sure.
Cool. Interesting side notes.
Yeah.
All right. Should we look into this fit one a bit? Who's still interested in that? Or should we try something else?
Well, what did you want to know about the fit one?
Well, I mean, maybe some of the stuff already got explained now with like just looking deeper into what did I want to know? I wanted to understand why these ones behave differently, essentially. But
why they were so bad, right? By comparison.
Yes. First of all, why do they like give us different output, and also why are they much worse? But I assume that's just because there's no. Well, it's still utilizing resnet.
Why don't you look at the docs
in this learner?
Of fit?
I just opened them. They
also,
should be
just
here.
something to note, Martin. We were messing with like resnet 34, resnet 18, the different
over here. Yeah.
So all of these like different. This is what I remember now. Like res LL was like, I think that was like another loss. So we were just messing around with it in like a non-educated way. We were just guessing.
Right. This is very messy. Yeah. No, right, but we were just one. I mean, we did. I think we did see that. Can we see this from anything here? That like the actual error rates were much higher in the ones that were not fine-tuned, right? I think that's something we
What
Can we
was
see
the
it
F
here?
for?
That's
I think that was fit.
fit. You know,
Yeah, and then
four
the
days
two-
ago.
The two with the F, they're much worse by like a lot. They're like a lot worse.
I think those were
What's the-
fit,
what are
and
the-
then LL was like lost learner or something. I
This
don't
is
know
such
what
a
we
beautiful
called it.
example for why you should take notes when you code anything up. Because
Right,
this is
I mean-
like not even like 2 weeks or anything. It's 4 days, and we have no idea what it was.
What's the headings? Can you just scroll up to see the headings?
What do you mean up here?
I mean,
Okay,
yeah,
gotcha,
the column
yeah,
heading.
yeah.
Okay, valid laws, train laws, error rate, and time.
Yeah, well, this was using resnet 34. This is clear, but then what is the F? No idea.
Right, but the res 34 and res 18, were we using fit or were we using
I'm pretty sure those were because the
think we-
first one was.
because we just kept
Sorry.
changing this like we didn't update the functions we
So-
didn't do new
So I think
cells. We just updated this. So there's no way
I
of
think
like going
so.
back.
Nick, if you remember, we did this like at the very end of our last stream. So
yeah.
I think we were just like playing around and we're like, okay, so next time we do this in the proper way. I think this was the plan for today, pretty much. It was like this is just messy. Let's do it properly next
Yeah,
time,
I
so that
would-
we
I would
actually have
just-
some sort of data.
Yeah, like scrap this and then start
Let's
from
not
scratch.
think about this. I think
Right.
that was the plan.
Yeah, these were so quick, right? Because at the end of it, we started doing the dog breed, and it was like 40 minutes to train or something, like something really.
So we
long.
switched over
So
to
we
this one,
switched over
yeah,
to
yeah.
this one. Yeah,
You can select a GPU and it should go faster, right?
it is.
Oh, it's
Yeah,
we are on a GPU.
Oh,
Yeah.
okay.
No,
No, that's the mistake we did the first time.
first one. It was like training for 2 hours, and we're like, why?
we were essentially watching it train for the first whole stream, and then we figured out
Yeah.
at the end that we didn't select the GPU.
Yeah.
So
Yeah, we went
now
back
we're
to the-
looking
we-
out for that.
We went back to the video, and Jeremy's like, this should take around 15 seconds to do, and it's like 2 hours later, and we're like, why is this still training?
So yes, we're looking out for the GPU. Okay, so let me just so we got some. Let's just run this again to see what a fit does. If we keep it somewhat. What do we do here? So this is we only just ran the one up here. Is that right? This one is the one we ran, and we did 3, 2. Okay, so let's forget about all of this and run just a simple fine tune. We get this results. If we do fit 1,
These are all on
compare those
different resnet. This is 18 versus the first one's 34.
this is also resnet 18. So I'm just thinking
Oh,
of
you're
these
just
two
starting
now.
these two? Okay.
Yeah.
Oh, that's funny. I have a model training too. I didn't even realize it, and it's still going after. Yeah, wow.
Are you on a
That's so
GPU?
funny. No, I didn't turn it on. It's been like 2 hours. I just ignored it though. That's
Well.
hilarious. Thanks, Google. Thanks for not terminating it. Okay, I'll terminate it. It's just hilarious.
Okay,
That
so
was a
this
big deal
runs.
when they started.
What? No, you
No,
say?
go ahead. No, I was gonna say it's a big deal when Collaboratory came out because they started giving free GPUs and you had to pay before.
Right, yeah. Yeah, it's really cool that you can go like over this whole course content. Essentially, you don't have to like you can do all the practical
Yeah.
exercises.
Yeah.
You don't pay
You
anything.
used to have to learn it. They used to have the best documentation for how to do everything on AWS. This is like 4 years ago when I first looked at their course, and it was a pain.
Yeah, this is so simple. It's really like you have the notebooks there, you open it up and you play around with it. This is
Yeah, it's
it's really
amazing.
nice. Okay, so
what
we
did
got
you do
some.
now?
So I just tried the different things. So this one, I'm not sure I ran this one actually. This might still be from last time. But
anyways, you don't need to run that one because you're redoing it, right? Oh no.
right, yeah. So it's
CN
probably going to be
learner.
the same. I'm
No,
just
you're
not sure.
but you're reinstantiating it now with you're calling CNN learner new, right? So it's making a learner,
Right.
brand new learner,
Yeah.
and training it.
Yeah, I think. And then
Because
we're just seeing the difference between fine tune one and then
and fit
one.
Okay.
Yeah.
Okay, got it.
But what Gilad's saying is right. Like we're actually running it on different metrics. Look, because here we're using resnet metrics error rate. This is still the same, but then we have a different loss function and the optimization function.
Yeah.
So we should probably just
keep the same if you want to have apples to apples.
Correct. Yeah. So we should do this.
What was the loss function default to?
A good question. Yeah, I'm not sure. Maybe we can figure that out. That would be inside of CNN Learner.
One thing I don't like so far about the way they do this book is they just import everything with star, and then I have absolutely no idea what functions came from where. That kind of annoys me.
He's actually talking about that, and he's talking about that a lot of people are maybe not gonna like that because generally it's like bad practice in Python programming.
Yeah.
But that he's happy with it because he's like he says it's like mixing up a bunch of different programming concepts, and the way that they set up the imports, it's not actually a problem. That's why.
Martin, you want to run fit before you go to that next tab?
Yes, thank you.
Yeah, I mean, it's just
it's pretty quick.
Well, I mean, I know you opened up the docs. I don't know if we were gonna go look through the docs and just to have this running in the background.
So CNN Learner, we have. So let's see, what's the default loss function? None. Optimization function Adam.
Yeah.
Who's Adam?
That's just the name of a person who came up with a good one. I'm pretty sure, or it's an acronym. I don't know which one. There's a paper for it. It might be the name of the person who did it, or it's an acronym.
A very important thing to debunk.
Yeah.
One sec.
And I'm done with it.
Adaptive moment estimation. It's an adaptive moment estimation.
Oh, nice! You actually saw.
I saw it in the results.
Nice.
No, I saw it in your results.
Yeah. Wow. Yes. You just picked up the important piece of info. Perfect.
Well, I've practiced staring at this stuff more than you.
All right. So this is now actually run on the same learner, but one time with fine tune and one time with fit. And now here's our results.
And Adam, which is adaptive moment estimation, I looked it up, is an update to RMS prop, by the way. An RMS prop, who doesn't think that stands for?
What's RMS prop?
I don't know.
Okay.
It's another one. It's another fit. RMS is, let's see. RMS.
Okay, while you do that, I'm going to have fun
looking
a little thing here.
RMS prop stand for?
Fun, useless side projects.
Why can't they just tell me what it stands for?
They shall not. Do you also have a little side project going on, Nick, at the moment?
I have my puppy running around at all the noise just happening in the background. I think someone's like moving in down the hall, so he's like running, trying to figure out what's all that sound.
RMS prop stands for root mean square propagation.
Okay.
So Adam is adaptive moment whatever, I already forgot, which is an upgrade on RMS prop, which is root mean square propagation, which is a specific version for basically doing backpropagation. So stochastic gradient descent is one kind. It's all about how they update the weights. It's all different strategies for updating the weights, but it all uses gradients. It's just like different kind of heuristic, hacky ways of doing it, and they all have different influences of how they do it.
Cool.
But it's all about finding that lowest one possible.
Method?
What are you doing?
What am I going to call that?
Oh, you're doing Markdown.
Cool, huh?
Yeah, it's got a little preview. That's pretty cool. I'm
So
impressed.
this was fine-tuned. So resnet. So okay, so we're gonna do. So this was fine-tuned, and what else do we need to record? We gotta know how many how many epochs maybe.
Close. You did it on one, right?
It was just one, yeah. So this was fit. I guess I can keep that info in here maybe.
Mm-hmm.
And then what else? We need to know which model we were using, right? No, wait, that's too much. 2, 3, 4. No, that's fine. And then it's gonna be the model, and that was resnet 18 for both of those. Resnet 18. Okay, so this is a little better organized than the last one.
Yeah, so
Am I missing
0.22
any?
train loss makes me think that it's 100% fitting all the layers. That's my guess. If I had to bet.
Mm-hmm. Mm-hmm. I see, yeah.
Or actually, valid loss is 0.44.
0.4.
It's really bad. Although 0.169 error rate's not that bad. I don't know. It's actually not that bad. I mean, comparatively, it's bad, but
for your like intuition, my intuition would be if we do the exact same thing with resnet 34, we're probably going to get a better result, right? That's just because we put in more layers, and there's this whole thing about deep learning, like you just add more layers and stuff, it's going to be better.
Well, if it's training from scratch, I don't know.
Let's try.
Maybe. I don't know. It could be. See, it's like if it's training from what are we training on, by the way? What's the problem that we're working on?
We're working on classifying. So we have like pictures of cats and dogs, and we're just classifying between those two.
Okay.
So it's a simple like binary classification, essentially. Yeah.
See, actually, 17% error rate's really not bad. That means it's getting it right. 83% of the time? I'm surprised that it does so well.
Oh, yeah. Okay, let's just for fun fine tune this with the same, but a different net. Then 34 fit. Okay.
So did you have to import resnet from somewhere, or that came along with the Fast AI star thing?
I think they download it when you run it the first time.
Yeah,
I think it happens in here.
Really? I thought it came with Fast AI. I thought
I'm
this
pretty
is
sure
part of
that
the Fast AI package. No.
I'm pretty sure that there's like the first thing that happens is downloading when you run this learner thing.
That makes sense.
So whenever you're using it, actually, it just fetches it.
But how does it know though? It's not a string. It's an actual variable name.
Oh, maybe resnet 18 and 34. I don't know. Maybe it's saved somewhere in like a config
Points
file.
to URL.
Yeah.
It's true. Like it must be coming in somewhere.
It has to.
Yeah. Let's see where we can. The docs. So one thing that I'm not very happy about, the only thing is that the searching in the docs is really weird so far. If I could, let's try. Like it does some custom Google search or something, which has really weird results. Right, as you see.
Yeah. I don't like
this is that's pretty annoying, but I never know what to click on when I see these results.
You end up just going to Google and searching there, and then you find it.
Yeah,
right?
it's easier. Yeah, and you just put Fast AI to it.
It's kind of silly.
Yeah, there's not much info here. Okay, so let's see. Resnet 34 Fast AI. That's a lot. Also.
Yeah.
Docs. And then we're back to these. Yeah, not sure. How does, I guess the forums are probably a better place to search.
I don't know. Well, one thing I want to say before I forget, since you're Googling things all the time, is the blog towards data science is like 95% not good. Just so you know.
Uh-huh. Which one? Did I just see it?
No, you didn't. When you're scanning, you're ever just searching for machine learning stuff and you're scanning,
This one?
Yeah, that guy, avoid, pretty much.
Okay.
I mean, there's always the outlier because it's people, right? So there's always the outlier that somebody is actually very good writer and took time to write something, but most of their stuff is kind of copy pasted, jargon filled, people trying to get their resumes padded kind of stuff. It's pretty bad.
Uh-huh. But it's a lot of people writing for it also?
Yeah.
It's not just one person? Okay, gotcha.
No, it's like a factory kind of thing. I don't know how they get their people to. It's got tons of people writing for them, and it's all pretty low quality, almost all low quality.
Okay, so we got our results here.
Somewhere it has to be imported.
So I was just it must be, but let's see. Maybe we can actually just call the docs on it. Why not?
Is that doc function a Google thing, or that's a Python thing that I didn't know about, or that's a fascinating?
No, it's something they implemented too, because it gives you these links to their own docs.
That's pretty cool. I like that. I like that a lot.
Sometimes it gives you a link to the docs. Here it doesn't actually, because I guess they don't have anything on the on their documentation. Resnet, but there you go. Look, it's got it's in there like this. You got a pre-trained false progress 2. You can pass something else in there.
Yeah, I'm in GitHub and I'm looking at that. It's under FastAI Vision models, and then there's like ResNet. There's a bunch of different ones. UNet, TVM.
FastAI Vision.
Yeah, if you go to their GitHub, like GitHub FastAI, and then I think it's FastAI again.
Yeah. FastAI again.
Yep.
And then
Vision, and they have the same text is obviously the models. Text, and then models, and so I just went to ResNet, that last one.
XResNet.
And it's got all that stuff on top. And then if you scroll down, the class XResNet.
This is sequential neural network.
Yeah. And if you go to, I think it's actually might be importing from, actually, no, I'm sorry. It's importing from PyTorch. So if you go back one to TVM.
Back to models?
To models. To TVM. There you see like torch vision.models, import ResNet, all that stuff. So
I see, yeah. Okay.
So you're getting it when you import FastAI.
What's the download then, though? I'm pretty sure there's some download that happens when you start running.
Yeah, I think those were like the images that we were, and it only ran once, and I don't remember seeing it run. Because it was like all the way in the beginning, when we, it wasn't on this cell. I don't remember seeing the download right there. Download PyTorch. Oh, maybe.
There it is. Look, yeah. Models. So it's just it's probably just got this URL saved somewhere, and that's what we're importing. Yeah.
Oh wait, was it root cat? Oh no, that doesn't make any. Never mind.
But yeah, we see that it comes from PyTorch. I guess that's we could have.
You guys know that PyTorch is developed by Facebook, right?
No, I didn't know that.
Yeah, well, they're developed. It's open source, but it's the Facebook team runs. They're running it basically. So they're the main competition to TensorFlow, and the academic community thoroughly has embraced PyTorch over TensorFlow. TensorFlow is the Google one. Anyways, I was just thinking about it because there was a really funny Elon Musk tweeted out like Facebook sucks, and I mean he's such a what I don't want to get into it, but the next tweet was just like the Tesla team, someone being like, "But we can still use PyTorch, right?" It's like, yeah, PyTorch is cool. It's funny.
Yeah, I the other day I went down like a Twitter rabbit hole on Elon Musk and how he's
Oh,
very
God.
yeah. It was
There's
it is so interesting.
I don't want to go there. I have opinions for sure.
Yeah. Maybe outside on a separate stream, we have like
Yeah, on a separate
opinions
stream.
on Elon Musk, and maybe we can invite him on Twitter and see if he'll actually. I wouldn't even be surprised if he jumped in for 2 minutes.
He's definitely a very online person.
All right. So we get some updates
So
going on
was it
here.
better?
So resnet, it took a little longer.
And you were right, though. It was better.
And it is, well, actually, this one, oh no, look, the validation loss is much better. What do you take from this? So the training loss is worse between the resnet 18 fit and the resnet 34 fit. But the validation loss is very...
My first question is, what are they doing with your data when you're doing this? How many data points do you have? And when you're calling fit, what is actually happening? Are they randomizing the shuffling without telling you that they're doing that, or is it frozen and they're seeing the exact same data every single time?
Good question. I do not have an answer.
Where's
so I
the
think
data? Where is the data
set,
even?
Yeah, let me see. So the data set is this.
That's
so
the
it's
path to the data set.
Right.
So data set? No, it's the
I think
DL,
it's doing it in here
DLS.
inside of the the
DLS,
data loader gets it. Yeah.
So the question is,
inspect the data loader a bit.
You're running it with the data loader, right? Yeah. Every time
Mhm.
you're calling the data loader. So what is the data loader doing?
Mhm.
What were we actually, yeah, go ahead and run that. But let's also look at what you actually ran when you ran data loader.
When I ran it up there, when I created the data loader, you mean?
I want to see the arguments that you passed.
Here.
So path get valid. So so valid percentage is, so that's the amount of the data that you're going to keep for validation is 20%, but you're putting a seed at 42. So that means to me that it's going to be the same every single time. So what's item TFMS resize to 44?
So it's transforms on each of the images, and I think in this case it's just making a 2 to 4 times 2 to 4 probably image out of all of them.
So basically, so then it sounds like the data is pretty static because it's got a random seed set. So that means it's reproducible. So then it's not just due to, so that's my first question. It's always, is it just data variation? You know, like if the data is just different, then that could explain everything. But
right. So we're assuming because we're using always the same data loader, and it has a random, like it has an initialized
the seed is set, which means that it's using a, you know how that works with the pseudorandom number generator and all that. So that's fixed. So that means that the data is exactly the same for training and validation. So then, then I don't know, just doing better. I don't know why.
But
worse, a little bit worse on training, but way
worse
better
on training.
validation.
Better.
Actually, but actually, having better validation loss than training is kind of like, I don't know. Why don't you run that again? Just see if it's reproducible.
That was our resnet 34 fit, which is happening here. Did I copy the right things? Yeah.
Yeah. That's weird. Normally, you should never have a better validation loss than training. If you do, then normally
right, because you have fewer fewer stuff that it is looking at, right?
Also, it wasn't trained on that. I mean, it's
right.
It's like doing better on the test. It's like doing better on the test than the study problems that you studied for.
That describes my university experience.
Really?
Yeah, I was always performing really good at exams. I don't know why.
But not good on the practice problems?
Not necessarily, no. Maybe I wasn't doing them enough, but generally I would learn a lot during exams and do pretty well. I don't know why.
during the exam.
I guess I was just like putting my brain to it when I had to.
Yeah.
All right, so
Now it's
this is different, completely
That's
different. Huh. So that means, what does that mean? So the fit we said is probably like always keeping the model unfrozen, right? Like it's just training across everything. Is that kind of our assumption? Yeah.
Well, that's our working assumption.
Yeah, right. So
We haven't really proven that yet.
but that's
yeah.
that's such a difference.
So what I would do in this case is I would do it like 100 times and plot the histogram. I mean, that's like, I mean, we don't have time for that, but that's the next step to try to get an idea. It's quite possible that it's the weight initialization, you know? So like because you're only running for one epoch and you're fitting the whole resnet, and resnet is probably like a pretty large thing. So it could just be that those initial weights are just, that's just, it's like rolling the dice wherever you start.
Right,
that
luck
really affects
with,
everything. Yeah. But if you trained it for long enough, they'd probably converge to the same place. But if you're only doing one epoch, then yeah, you're not in a very good
That makes
spot.
sense, yeah. Yeah.
One of the early breakthroughs for deep learning was this thing called the restricted Boltzmann machines, RBMs, I think. They're not around anymore, but their whole thing was just getting the weights to a decent starting position to start the training, because then they could get good results. It was just computationally too expensive to it just took too long to get the weights to go to where they need to go with the amount of data they had. That was just before GPUs. The GPUs was like the next big breakthrough, so you could train faster. But before that, they had this thing called restricted Boltzmann machines, which all they did was get the weights to like a good starting place, and then they would do the normal training.
Yeah, you always see like here too, between the first few epochs, the difference between the training loss, the validation loss, and the error rate are like there's a huge difference. Compared to like the 5th or 6th or 7th or 8th epoch. So
yeah, it should converge. If the math works, right? So it should converge to like a steady state essentially.
We just don't know how many epochs you would need for that.
No, and then at some point
it would be different.
Worse. Yeah, at some point it'll start getting worse too.
Okay. All right, so we're not going to run this many times. Any ideas of how we could like figure out more about fit, except for searching in the forum, like to figure out whether it's actually, that's probably the best way to go, right?
What are the docs? We didn't look at the docs yet, though, did we?
We did, but it doesn't say very much to me. Where was it? Is it here? Is it here? Who knows? There's way too many things I have open. There it is.
We got sidetracked, yeah. So what does it say? Fit self-model for n epochs using CBS. Optionally reset opt. So opt would be the optimizer, is my guess, right? What does CBS stand for?
CBS.
Current batch size?
The list containing all callbacks.
Callbacks. So callbacks is when you tell it to stop normally. I don't know what callback. I don't know what they're thinking about callbacks, but I've always used it when I did deep learning. Callbacks was like how you told the network to stop training. Like if you didn't want to set number of epochs, you would do a callback that would say, okay, if this thing happens, now stop. So basically, if the error is not decreasing enough, stop. Or if the error gets worse, stop. Or like, oh, there's lots of callbacks. Okay, wow. But yeah, all these different keywords, so you call back at all these different locations. So like, after this thing happens, check that thing, kind of. So it's a way of like monitoring. It's a way of monitoring the training process, so that at any point you can essentially stop it, or you can log or whatever you want.
Okay. So
let's scroll up again for a second. So let's read it again now that we know
this
what
one?
GPS is.
Oh yeah,
Yeah, on this one.
I don't know where the other one was. So learner.fit, I think. Learner.fit. Okay, here we are.
So for n epochs using callbacks. Okay, so it fits the model for that number of epochs using the callbacks. So whatever callbacks were provided.
Mm-hmm.
And then I'm pretty sure reset op would be reset the optimizer. And I don't really know what that means.
See what they're
Reset the
saying.
optimizer.
Oh, this actually doesn't have a explanation up there.
I'm not really sure what resetting the optimizer would do. I guess optimizers must they must carry some information around with them, I guess. I never really studied the fancy optimizers.
Colorful result table.
But I think we can assume that I guess the only question is, does it wipe the weights out or does it train from their current position?
There's
Yeah,
some
click on that. Yeah.
explanation at least. You're not being very fast. Are you? Okay. A Boolean flag to indicate if the optimizer associated with learner object needs to be reset. Is that exactly what you just said?
But what does it mean to reset an optimizer then? That's the question.
Right.
So what does it mean?
Yeah,
what does it mean
that's
for an
the
optimizer to be reset? Like,
yeah,
anything
I
more?
was blanking for a moment while I was reading it, but you're right. That's just essentially what the variable name says.
Yeah. What does it mean for an optimizer to be reset? That's the big question.
Okay, let's try that.
I think it probably not important, but I mean, it's important to somebody. It's a flag, right? So it's sort of, I'm sure it means to like start from learning from zero again. So
Optimizer.
So one thing I know is that optimizers, like one easy thing optimizers do is they have this idea of momentum. So when the learning rates adjust, they'll adjust more in the beginning. So learning rates have a schedule. So normally, like the basic way is you just set a learning rate and you just use that rate the whole time. But then there's these more complex optimizers that have scheduled learning rates that will change over time.
Mm-hmm.
And so probably resetting it just is making sure that everything starts at zero for your because when you fit, maybe you want to continue fitting from where you left off. Like you fit for a while and you stop and you want to start again. So I don't know. State dict, load state dict, reset the state. Yeah, I'm sure it's just like the optimizer will have all kinds of different options. One of them is momentum, is the one I know about, which is like it's this technique to.
Is it in here?
I don't know.
The best example is the momentum calculation. Some of the optimizer, what was that class?
Callbacks.
No, not callbacks. Thanks. Can be functions updating the state associated with the parameter, so not just stopping it, but also like just doing something with it, depending on whatever happens, I guess. The state can then be used by any stepper. The best example is a momentum calculation. Okay.
Yeah, so a stepper is the update that you're doing. You're taking a step in one direction or the other direction.
Mom.
Yeah. I wouldn't worry about mom is for momentum.
We saw that before because I already found it funny earlier, so I remember finding things funny.
Yeah, the idea of momentum is this idea of for getting stochastic gradient descent to work better, basically. It's because the idea is you don't have a Gradient descent works like it's proven to work if it's a convex optimization problem where there's a bottom that you're trying to optimize for. But the problem is with these crazy networks that we're making and these loss functions, like we actually don't know what the landscape is, so you can get stuck in a local minimum. So you're like in a valley, but it's not the lowest valley, but it's a valley. So gradient descent will just get stuck there.
Yeah.
It'll just get stuck in that kind of valley that's up high in the mountains, and you want to get it to the bottom. So the idea of momentum is that like it sort of won't get stuck. It'll hit that bottom, but then because it's got all that momentum, it'll like roll its way out. So it's a mathematical way of trying to force gradient descent to find a better optimum, essentially.
And it doesn't just like randomly reinitialize it and then figure out whether it goes somewhere else that's deeper. It just like it stays with this, but essentially gives the ball a push.
Yes.
And then it rolls out of that.
Yes. Yeah. The randomized thing you described is a different algorithm. That is an algorithm. That is an optimization algorithm, but it's not even gradient descent. It's like simulated annealing or something like that. It's like something.
But it would still do some gradient descent. Like the way I was imagining it is just it does gradient descent to get stuck somewhere, and then it does it somewhere else, and then just compares which one is the deepest, essentially.
Yeah, I see what you're saying. Yeah, but that's not. Yeah, it's like random restarts, basically.
Yeah.
Yeah, that's sort of just like running fit over and over again, I guess. Is it? I don't know. Random restarts is definitely a thing for a lot of optimization algorithms. I don't know if random restarts is used in gradient descent or with gradient descent. I'm sure someone has done it. Or maybe they just found that you don't really need to do it. I'm sure they tried it at some point. Random restarts is like a well-studied like solution for any of these problems where you where you can get stuck in the wrong place. You just do it enough times to see which one's the best. It's a very common approach.
Makes sense. I forgot what we were doing.
We're trying to figure out what fit does. If it's wiping out what is it? It's training on everything.
Okay,
that's
so
clear.
This is the right page to be on, right?
But is it starting with random weights, or is it starting with the weights that are already there from the model? That you got.
Is it just using the architecture of the model, or is it right? Is that the question? Is it just using like these and these and these layers from ResNet 18, or is it using the weights, the learned stuff?
Yeah.
Okay. I mean, I'm gonna give this another try in the forums because that sounds like a searchable question.
But see, learner.fit itself just fits. I don't know. Go ahead and ask it there. I would guess that it just uses the weights that came along with ResNet. That it doesn't wipe them out.
Wait. So you're saying it does use them?
I think so. Why would it wipe them out? You'd have to reset them somewhere.
But then,
because it's just.
I still have a little block and understanding there. So then, what's the difference to like that's still transfer learning then, right?
Yeah, it's just transfer learning without the fine tuning, basically. You could test that. Can you run fine tune with freeze epochs equals 0, so it doesn't fine tune?
Okay. But we're not going to know whether it's the same because we keep getting these different results, right?
Yeah, that's true.
I guess we could do 10 epochs and run it with freeze.
Well, 10 is a lot. Why don't you just do 3?
3, okay. Maybe it converges already. Then we do this one also with 3.
Yeah.
Yeah? Okay.
Yeah, try that. Yeah.
Does fine-tune freeze any epochs by default?
Yes.
One
by
default.
I think this makes sense that fit is getting pretty, because it's not getting the worst. If it was completely random weights, it would just be like terrible. It would not be getting 83% accuracy.
That makes sense,
whatever it's getting. So it's probably random weights on the last 2 layers that aren't getting fine-tuned at all. the ones that you got appended when you took ResNet.
Yeah, that makes sense.
What was the WD? So like there was a few parameters.
Here?
Yeah. What is WD equals none? So LR is learning rate. What is that? The attributes of learner.
WD is
Weight
the
decay.
default
Weight decay.
Okay. So if you go on, I looked at the code on GitHub FastAI for learner.fit, and
is it helpful? Should I bring it up?
you could. I mean, it's obviously you have to like bounce around a bit more. It's learner and then
learner.py, I assume.
No, go back to FastAI. Scroll all the way up. FastAI, the second one. Yeah, and then scroll down to learner. And then it's on line 198.
Is it self.fit? No.
Def space fit.
Ah, right. So it's actually not a. Okay. All right. What
so
do you,
nothing
what did
about
you see
like.
here?
Well, that's what I was asking about, like what WD is, like this weight decay. But here's like if it's none, then it sets its own weight decay. But I don't know what weight decay is.
Right.
So I was thinking here.
It's another version of that momentum kind of thing. So it's
just changing the. Yeah.
Yeah, it's like a learning rate on the learning rate almost. That's really what it is. Weight decay, it's just like as the learner, it's weight decay. Actually, maybe I don't know. Yeah, actually, no, I'm not sure because it's not learning rate decay. It's weight decay. So what is weight decay? I thought it would be.
It also looks like when you initialize learner, it does pass some default momentum. Like mom's is not like none.
What? Why apply weight decay? That first one looked good.
Did I open that one? Yeah. I did.
Oh, you did?
Yeah, I got it here. Why apply weight decay? That's the one you meant, right?
Yeah, that one. Yeah.
What is the weight decay loss? Weight decay is an additional term that causes the weights to exponentially decay to zero. What is it that we're hoping to achieve via applying weight decay? I tried Googling for this, but mostly tend to talk to I2 regularization.
Oh, it's actually an L.
L2 regular. Okay. They're mathematically identical. Smiley. In the last couple ML lectures I've gone into this more detail. Check them out if you're interested. L2 regularization, does that ring any bells for you?
Yeah, I know what that is. So they're mathematically identical, huh?
That's why he says.
Yeah, so basically then the idea is, so regularization is the idea. Did you guys learn what overfitting is yet?
Yeah.
Yep.
Did you? Yeah.
So regularization is this, it's actually weird. Regularization, I think it's technically today, it means anything that fights overfitting. But it traditionally, in my book, started off as this L2 regularization, which is this, basically the idea is that like, it's mathematically identical to, then I'm assuming it's the same thing, right? So then it means basically you are constraining the size. Just Google L2 regularization. We can look at the equation. It makes the most sense if you just look at the equation.
For you.
Well, I'll be able to explain it to you if I can look at the equation.
Towards data science, no.
Avoid. Just type equation. Yeah, mathematics. That's a good one. Wikipedia.
But probably this is fine, right?
Yeah, that's fine too. So L doesn't have to be L2. It's just that any one of these is fine. So wait, no, scroll up. I think we can just look at the general equation for regularization. Idea of regularization. L2 you can ignore actually. It's just the idea.
Do you see it somewhere?
Just scroll down slowly. Yeah,
You like that?
Down.
Is that good?
Yeah, keep going down. Keep going.
Slower?
Okay, so wait. Now I think we can look at this.
This
Yeah.
one?
Okay. These Tikhonov regularization. This is the basic idea. Okay. So you're trying to minimize this function basically. So this sum, it's a minimization of this sum of whatever. But this plus lambda w that, or plus lambda f whatever, that's the regularization term. So.
This doesn't tell me anything when I look at it.
I know.
Like
So okay, go back to your. I'll think about it while you search on Google for a better explanation.
Got some medium there, hit and miss. Math stack exchange could be useful.
Try scikit-learn, sklearn.
Okay.
Regularization. They have good documentation. ML cheat sheets is also good too. Oh, another really good one is Chris Albon's flashcards. Actually, that's a really good one for ML terms. He has these flashcards. Chris Albon, ALBON. Yeah, and then regularization of flashcard. Try that. That might get a hit. I just don't know. I feel like they're free. Nothing on regularization.
Validation. Should I look pictures?
I don't know.
L2 norm, is that it? No, that's something else.
Yeah, well, L2 norm is the type of regularization that we're doing with this weight decay. So the L2 norm is just that I can explain. L2 norm is just Euclidean distance, but generalized to n dimensions. So it's the distance between 2 points. It's really just like the distance between 2 points. That's all it is.
Okay.
But it's generalized to n number of points, or n number of coordinates is the better way to put it. So like in a two-dimensional graph, you have 2 coordinates for 1 point. In a three-dimensional graph, you have 3 coordinates for 1 point. In n number of dimensional graph, you have n number of points. I mean coordinates for 1 point. So that's why it goes up to the xn there. So it's just the distance between 2 points in an n number of dimensions. That is the L2 norm, which is also called the Euclidean norm. But now we're doing regularization using the L2 norm. So we're using L2 norm to be the distance metric. It's a distance metric. It's telling us how far apart 2 things are, and it's a way to you're using that to perform regularization. But the idea of regularization, I think ridge regression. Look at ridge regression. I think if I remember right, yeah, that one. Shrinkage. Yeah, this is actually really similar. This is ridge regression this is weird. See, machine learning has all these other names that mean the same thing. So ridge regression is like doing linear regression.
Wait, this just took me somewhere else. Sorry. Ridge regression is linear regression? Oh no, wait, it's not loading better.
No, it's because it's from someone's quiz thing.
It's not like an original one.
It's not actually an original though. I think he sells these cards. I'm not sure. Oh, what did scikit-learn get us? Yeah, they'll tell us the same thing. The scikit-learn search.
Yeah, I just have too much open, so I'm not sure where it is. Just a second. There we are.
Yeah, ridge.
This one.
Ridge. Yeah, that one. Yeah. Let's look at that one.
Our training is finished too, so we can also peek at these results.
Okay, yeah. So this is linear least squares with L2 regularization. So if you open up read more in the user guide, they might have some picture for us. But so linear least squares is like you can solve it with gradient descent. Okay, so you can think of it as a very similar problem. It's the mx plus c problem. So you're trying to, so this big xw minus y, now, yeah, this makes more sense to me also. This xw minus y, that big X is your matrix of points, and then the W is your weights. So it's just your WX, your weights times X.
Okay.
Minus Y is the loss, so that's minus the label. So you can just think of the XW as the prediction, like the prediction factory. The XW is just the matrix multiplication that's getting a prediction.
Are you?
This is a loss.
I'm getting a lot of extra noise from your mic. Are you touching it maybe somewhere?
No, could be my fan, and I turned the way I was facing. How about now? Is that better?
Yeah, that's good. It was just like some, as if you would be moving it around a lot or something. I'm not sure.
I don't know what I was doing. But the XW is the prediction, okay? The minus Y is the loss. So you're comparing your prediction to your loss. Now the squared thing, that is just the loss function. That's linear least squares because it's the norm. It's the L2 norm squared. So it is
what's that syntax even? What's this?
Actually, the double
square.
bar. Yeah, it's weird. Double bar is norm, and then the squared, so you're squaring the norm, and the lower two is that it's the L2. So it's saying I'm taking the norm, and I'm taking the second norm.
So what the norm is just what's that even?
The norm is just it's a generalized function. It's a function where you can plug in a number, and the number can be anywhere between 0 to infinity, or no, 1 to infinity. 0, they do talk about the 0 norm, but it's not really a norm. I studied all this, and I actually made a video for my machine learning course. You have access to my course, right? You should watch the course. I should just show you that video. I studied all of this quite a bit to make that video for it. But anyways, it's just the distance metric, okay? The point of this picture isn't actually important to understand the math of that first term. Just know that it's the loss function, okay? It's how bad you did, okay? And now so normally what we do when you're doing linear least squares, ordinary least squares, or just gradient descent, is you're just saying, okay, I want to make that W, the best W, to minimize this loss. Okay? That's what you're doing without the right-hand term. You're just saying, I want to find the best W that's going to that's why it's min W. This is actually wrong. I remember I got angry about this. It's not really min W, it's arg min W. You're not minimizing W. This is bad notation. I should make a pull request for this, because this is really wrong. It's really not. I remember this very clearly now, because I went on my other Slack team and I asked all the other data scientists, what am I missing here? And they all told me that it's not minimizing W, it's minimizing, you're not trying to minimize W, you're trying to find the argument W that minimizes this equation. So you're trying to minimize this loss. You want to minimize this equation, but you're trying to find the W which does that. So you want the W which minimizes this equation. Okay. That's the whole point. And if you think about neural networks, it's the same thing. It's the weights which minimize that loss function. Right?
Yeah, that makes sense so far.
Okay.
I mean,
so
doesn't really connect
exact
with
same. But now we've done this weird thing with this equation. You have plus alpha W, and you're saying I have to minimize the equation of the loss function plus alpha W. Alpha is just a parameter. It's the decay parameter. It's the regularization parameter. It's a tunable parameter, just like the learning rate. But so if you're trying to minimize this loss, and basically, but you're also adding to the loss function W itself, or some scaled version of W, then you're kind of screwing everything up, because if W gets really large, if let's say a W at 1,000,000 minimized this function, originally I would be totally fine with that. But now if W at 1,000,000 gets me a really low rate, well, I have to also add 1,000,000. So now I'm not going to prefer that as much as a smaller W. So it's a penalization term on W, and it basically says keep W small. That's what it basically
Mhm.
says.
Mhm.
And
Okay.
the reason you want to do that is because if you allow W to get really large, then you can get overfitting.
Mhm.
And that's what you can see down there on that graph with all those colors. So when alpha is really small, which is 10 to the negative 9, then basically we're not penalizing much because that W term that we're having on the right side will get very small. So the smaller alpha gets, the larger and smaller the weights can get. They can express themselves more. And the more the weights can express themselves, the more you can get in that range of overfitting. So when you apply weight decay, if he's saying that weight decay is mathematically equivalent to L2 regularization, this is L2 regularization, then that means that you are telling the network, I don't want big weights. I want small weights.
Okay.
Because I'm worried about overfitting, basically. So it's a way of baking in anti-overfitting to your network itself. Kind of, sort of.
No, I mean, I think I get the main point. I don't necessarily understand how it's implemented, but I'm fine with that for now.
So we were on fit when we saw this seed. We were looking at WDS, and that's why we found weight decays.
We looked, yes, we were. No, learner.fit, yeah.
Yeah, WD.
Yep.
We wanted to know what WD was. I think we were in the actual.
Where there?
I don't remember where we were.
Learner. Looks like learner that should take us to learner.fit, but I don't think it does. Learner.fit. There it is.
WD.
Yeah. So it's not applying that.
But if you wanted to, you could.
I could. Okay, go. Nice.
So the big question was, does it reset the weights of the model? And I think it absolutely does not. Because you built fit just operates on a learner. Fit is just a method that runs on any learner. It doesn't have an option to reset the weights. I think if you want to reset the weights, you have to call something else in the learner, some other
right, because when we're downloading resnet, it just comes with the weights already.
Yeah,
right?
Exactly. That's the point of resnet.
Right,
there must be like learner.weights reset or something like that. Some way to reset the weights or reinitialize the weights.
Okay,
so how did these compare?
How did this compare?
Oh wow, yeah,
very different.
Very
Seems
different.
like a similar difference to strange.
Well, maybe there's my hypothesis. It's gone. Fine-tune did way better.
Well, I was gonna say, like, it is getting better at a similar rate, though. It is almost like the first two were, the second epoch was twice as good as far as like training loss in fine-tune, and then it did get twice as better in fit, and then it's slowly, like, I guess between that and the next, like, epoch 1 and 2 in fit, there's less of
it got worse though on epoch 2.
Yeah.
The validation got worse.
Yeah.
Oh, it's overfitting. Okay. Validation loss got worse, but the training loss got better, so it's overfitting.
Yeah.
And the error rate got worse as well.
Yeah,
that makes sense.
That follows from the validation loss getting worse.
And here,
so overfit.
It's not doing that.
No.
Yeah.
But it's only.
It's marginally improving, but actually not just marginally here. Same error rate.
Super interesting.
Huh.
Can you scroll up, Martin? What were the additional parameters we were throwing into learner for fit to have such good results in like 4 days ago?
Oh, okay. I see what you're saying.
Because we were doing some other stuff, and
we were specifying like I think that's below that actually. Put all that stuff. above it. Here we are. This is what you're looking for, right?
Yeah, maybe
So
like
I just
including
this
like
is
the
what we
loss
did,
and the
loss
optimization
function.
functions. Yeah.
But so that did we say that the learning the fine tune does that automatically or not?
Does what automatically?
That it includes like an optimization function and an error rate and
The
loss function.
I mean, it has to. It can't function without it.
Right, it needs a loss function. What's the other thing?
It needs all the. It needs all those.
It's all of it.
Yeah.
So
It has
what
to
are
be
they? I
multi-something.
guess. But so so you're saying that also the fit has a default for those.
Yeah, it has to.
Okay, so what are they? That's so wait, fit. We're not passing anything. This is I'm getting confused. Wait a second.
So it's not fit and fine tune. It's the actual learner.
It's the right.
Yeah,
okay, it's the
yeah.
learner.
That's
right,
the point.
that's
The
why.
point. The point
Okay,
is that
okay, I
the
see.
learner. The learner comes with something.
Right. So we're not changing anything about that. That's the same for both the fine tune as well as the fit. That was our first step
No.
of.
But scroll up for a sec. When we made these both run for 3, you created one as a new learner, and then they ran sequentially, right? Not parallel.
Sequentially, yeah.
So that to me, I would.
Oh.
Yeah, it's
Yeah,
continuing
you're
where
right.
it left off.
Uh-huh.
So I would add another.
Oh my god. Yes, of course. So we'd have to make that again.
Yeah, you'd have to make it.
So
again.
you think it actually fine tunes and then fits it after on the same?
Oh,
yeah, probably.
Why wouldn't it? But why did it get so bad though? That's what I don't get.
It would make more sense if it got better the second time, right?
Yeah, it would make a lot more sense if it got better. Yeah.
So,
did that go run at 20 though? Is that it has that play button next to it? What's its output?
What do you think?
See, the other one says 19, but the one that you're on now it just says play.
Yeah,
it did run. Let me show you. Yeah.
Oh, now
See?
it's 20.
Yeah. It just doesn't show it for sometimes. I don't know why. When you're hovering over it or something. Okay, so
yeah, it doesn't make sense to me that it would get worse though. I would think it would just get better.
I'm not gonna run this one again because that was the first one we ran.
Yeah.
Was it though? Jupyter Notebooks? I'm not sure. No, it must be because no, it
You're
actually
instantiating it. You're creating it right there.
But the thing is, like, maybe I instantiate. No, I didn't instantiate a 34 before. Right?
Even
we were
if
just
you did,
learning.
Wouldn't it overwrite it?
Yeah, it would overwrite it. You're making the variable right there.
Right, but what I'm saying is like before I didn't have this one. So if I actually ran this one before, learn34.fit, and we already had a learn34 sitting somewhere, then it could have used some old one.
Yeah, but that's why it's 1920. That's why I wanted to see that number.
1920. Okay, I see. Nice.
So we knew it came right after 19.
Right, you're right.
That's why I wanted to know what number was on that one.
So we don't need to run this one again. I can run this one again with a new learner, and then we have another thing to look at.
Yeah, but to be honest, like the amount of data variability we've already seen, I just don't know that we're going to really be able to get anything conclusive from this experiment.
Yes, I see what you're saying. It's not a good. I wholeheartedly agree that it's not a good experiment setup that we're doing here.
It's just changing too much every time. Everything is changing too much every time.
Yeah. Oh well.
So what are the arguments for CNN Learner? All the options. Maybe we can look at the that ResNet 34. What position does that sit in? And what's the keyword for that?
I guess I can't do it like that. I'm gonna just look it up.
Yeah, because it's running another cell and let you play with it. I like that they have that integrated search Stack Overflow on their
yeah.
collab. That's
Me
pretty
too.
cool. I like that.
Is that a learner? Would that be CNN Learner?
Well, yeah, CNN Learner is a specific kind of learner. So it would be a subclass, I guess.
There it is. Learner convenience functions.
Arch architecture.
That's where we're passing into ResNet. Data loaders, that's the images.
So on this
and the
one,
labels. Yeah.
No, never mind.
Number out, pre-trained, true. I guess this is something we could pass if we actually wanted it to maybe get rid of the weights, right? We could say pre-trained false.
Yeah.
That might actually do it.
But it says if normalized and pre-trained are true. Oh, okay, never mind.
Wait, so no
what
loss
is
function.
normalized default to?
Normalized defaults to true. But what's it? It also seems like it defaults to having no loss function. Didn't you say that doesn't really work?
Yeah, I don't know how that would work. I mean, how can it do anything? Unless all other arguments are passed to learner. Maybe learner comes with a loss function.
But and then it passes it on, and
no,
it says it at the bottom.
Yeah, learner's loss function is also none.
I don't get it.
Yeah. But actually, like if loss function is none, it says, what is this here? Get attribute data loaders dot train ds loss function. So maybe it's in the data loaders.
It gets it from the data loaders. Then.
And then, I mean, it does say like if it still can't get it from the data loaders, it will prompt you and say it can't infer a loss function. So maybe in
so it's trying to find it from some. Yeah, must be.
Did we define something in there?
I don't think we did. I think it was
when but it was already in there.
It seems like it had to be.
Label function. Resize. Not explicitly. I mean, it could be in all sorts of things in here, obviously.
I got a feeling it defaults to something simple.
Mm-hmm.
And just, implicitly passes it along.
There's definitely a fact that it has to have a loss function. Like nothing can go without a loss function.
Data loader. Timeout batch size. After, before, after, blah, blah, blah. Doesn't say anything about it. BS none. Just saying.
It's probably something like defined in PyTorch. Like there's got to be a default data loader in PyTorch.
I don't think data loaders are PyTorch things. I think that's...
Yeah, it is.
It is.
Compatible with PyTorch data loader. Yeah.
A lot more callbacks and flexibility.
See, the thing is, FastAI is all designed to like kind of make you not have to think about this stuff so much. You know?
Yeah.
Their whole thing is that like you just use our kind of cookie cutter stuff and adjust these few things we tell you to adjust, and then you can make really cool stuff really fast. And it's mostly true. But what we've been doing is asking a lot of questions, trying to understand its guts, and it's got a lot of options.
Wait, hold on, Martin. If we just humor me for a second.
Okay.
Did we scroll down the page to see if our answers were lower in the documentation? Because I think I remember somewhere in the forums, someone was like, "Just keep watching. Your questions will get answered at some point in like the upcoming lessons." So I think we're just spinning our wheels and like wasting Google's resources on Colab,
Maybe
trying to figure these things out on our own.
So Gilad, like one thing that we learned also like while going through this course so far was that I guess especially me, but both of us would like start discussing, like coming up with questions about things, and then talking about it for a bit, and then we would scroll like one cell down, and then the answer was there, which I think just means it's like really good learning material, because essentially it just brings up the question, you know, and you're like, oh, like why is it like this? And then you keep reading, and then you have the answer there.
Literally
So-
every time, multiple times per stream.
It happens a lot.
Hey,
but now we're kind of
better this time on your Learn 34.
Does it? Is it this one?
Not bad.
0.7. I didn't actually record the last one, so
The last one's right above.
each other. No, just scroll up. They're pretty close to each other now, right? Which is what we.
Oh, you're right.
Well,
that's what we
that close.
expected.
No, now
Oh, interesting.
the second one is better than the first one, right?
No, the second one again overfits.
Yeah.
Here. And that was the same though. Like also when we ran it before, but it seems to be closer, right? Because before it was like somewhere at 0.1, if I remember correctly.
I don't remember.
Yeah.
At what point, Gilad, can you just assume that these numbers are like virtually the same? Like how many leading zeros does it have to be for you to be like, you know what, whatever, it's the same?
It just depends on the product. Like it always comes down to what you're trying to do with it.
So in this case, for like cat or not cat, this seems like it's almost, even as it's getting worse on that last one, it's essentially 99% correct. 99.3% correct.
Yeah, it's great. Isn't that good enough?
Well, that's what I'm saying. It's like, because that, I maybe, you know, this isn't using, I'm just thinking like the gradient descent, right? Where like you're kind of going past that parabola and then it gets worse and then you go, you know, it just goes up again. So we're essentially doing something similar to that, right? Where like if you just keep training, it's going to get so good that it may get worse, but even in this case, that little bit of it getting worse is still pretty good.
Gradient descent should get to a steady state where it doesn't really move anymore. But what's happening is that it's actually getting better and better. That's why the training loss is getting lower and lower. But it's overfit. So then it's learned that it's basically started to learn noise in the data is an easy way to think about it. And it's learning the noise, which isn't the signal, and then that noise is just specific to those particular training points. It's learned it too well, and it's not generalizing. And so that's why the validation loss is getting worse. But gradient descent itself is just optimizing onwards. It's just marching forward. It doesn't care.
Got it.
But we're over optimized to that training data. It's like you learn details that aren't relevant to the problem. But you don't know any better, so you think they are. So but you know, the Andrew Ng famously said the difference between a successful company and a unsuccessful company is, you know, 5% accuracy or whatever, something like that. So from like 99% to 95%, that's like a busted startup versus like a boom startup. So it really just depends on what you're trying to do and what your tolerance for everything is. And when you're trying to, I mean, that the question is the right question. Like when does it matter? Like these are just numbers. Like you have to put them in context, right? So it also comes down to another question, which is, do I think the data that I have is representative of the data that I'm going to get? And that's a huge question. So, I mean, basically, if we're doing a cat detector, it's like, do I think that the cats that I'm testing on or training on, all of the above, is a good representation of the kinds of cats people are going to use when they use my app? And if I'm not confident about that, then I wouldn't be very confident at all.
Sure.
I would. So you have to ask You have to ask these kinds of questions a lot.
Mhm.
Very, very simple, practical questions. But it's very easy to get lost in just looking at the numbers, and I think that's a big mistake.
So just to clarify, the boom and bust 95 and 99%, you're saying that the 99% would be bust and the 95 would be boom.
No, the other way.
The other way.
99% is better.
Okay.
Boom
So,
is good, right?
Well, because I've heard I didn't know like the full context of what Andrew was saying, because you're like, for the startup wisdom is like, if you're not really embarrassed with the first product, you've shipped too late. So I kind of interpreted what you were saying as like, I need to get to 99, but by that time, like, you're getting like it's
that.
too
No,
late.
No.
95 is good enough, and
I understand. Yeah.
Yeah.
No,
Okay.
he meant
Gotcha.
it. He meant it in the your app sucks because it doesn't work enough, enough. So like, basically, like, people will just get frustrated with a certain amount of error in the application, and so if it's buggy enough, like early days with Siri or whatever, like, people, it was like, whatever, you can find your way around all these things, but like, basically, if it works most of the time but not all the time, people will just think that it's crappy and they won't use it. That was his point, I think.
Mhm.
So, but if it works 99% of the time, but it makes a mistake here and there, people will be like, yeah, it's not perfect, but it's pretty good. That was his point.
Gotcha.
But I mean, that's just one quote. It really comes down to like what the domain you're in. I think I always think about it like that. Am I in a hospital? Am I in a bank? Am I in a convenience store? Like, am I trying to sell ads? Like, what am I trying to do with my machine learning model? And then based on that, I have to be very, very thoughtful about what metric I'm using to evaluate. Like right now we're using accuracy, which is error rate, which is the inverse of accuracy. But I mean, that's not a good metric if you're trying to detect cancer. It's the wrong one. So you have to really think about how you're evaluating it from a lot of different angles.
Sure.
What's just out of curiosity, what would be a different error rate that you would maybe choose for predicting, like identifying cancer or something like that?
So you want to pay a lot more attention to like false positives and basically false positives.
Okay.
So
low amount of false positives, for example, would be an error rate. Would be a metric.
Actually, I wouldn't want any false negatives.
Negatives. You don't want to say that someone. Yeah. You don't want to say someone has cancer when they don't. Yeah.
I don't mind telling you that you have cancer when you don't. That's okay. If I tell you have cancer and you don't, it's okay, because you'll stick around and we'll do more tests, and eventually we'll figure out that you didn't have cancer and you go home safe. The scary thing is if I tell you you don't have cancer and you do, that's a false negative. Right. Because a negative in a cancer test, it's always positive as cancer. So a negative is like, yep, you're fine, Martin, go home. That's like the dangerous thing.
Right.
You don't want to let that happen. So you want to optimize for having a very low false negative.
Does that have a name? That metric?
Yeah, it's I think it's, well, it has a bunch of different names, but I think it's I think it is, well, I mean, well, there's the false negative rate. That's the name for it. But I think in statistics, it's called like the sensitivity or the specificity or the.
Right. Oh, yeah, I've heard these terms.
Yeah, they're all out there. But I just stick with false negative rate because the sensitivity and specificity mean nothing. I mean, you can make up what they mean, but false negative rate is pretty clear. That is a term, false negative rate, FNR. You can look that one up.
Cool. Makes sense. All right, guys, I'm kind of like at the end of my brain power for this.
I gotta go to sleep too.
Yeah, and I think, I mean, that was interesting.
I mean, I think
I learned a lot by looking at these things.
Yeah, this was more useful, just to be able to like pick your brain and just bounce ideas off.
That's fun.
Than us going like, well, I don't know, and then like, oh, well, let's just scroll down a little bit, and then we still sort of understand it.
I think we've gone pretty well with just scroll down a little and then just first talk about it, then scroll down a bit. But this is definitely more helpful.
It's really interesting because he's teaching a very complex thing in a very compact way. So
the thing is also that this chapter that we're currently still on and have been for a couple of streams, like I said at the beginning, is like the one where he says, okay, like now, because what you said is exactly true, that a lot of this fast AI is like just do it very simply and get good results. And we did that at the beginning, right? We ran a couple of things and it worked. It was fun and we got some good results. And we're actually at this point where it's like, okay, so now try to understand a bit deeper what's going on. That's why we went down this couple of rabbit holes also. So I think this was like an interesting session with you, also like to get over this in a conversational way, more from a different perspective. I like it.
Yeah, totally. Yeah, thanks for taking the time and like being on the stream with us. And
so what we're
explaining all this stuff. This is great.
So what are we gonna do next time? Huh?
What are we doing next time? Oh, I don't know.
Because I kind of want to like take a step away again from this unraveling stuff and just more towards using some of the stuff to build things. I think we've been like for a couple of lessons now just like trying to learn and understand and go deeper, but I think it would be fun next time to actually like just use fast AI to build another classifier or something.
Yeah.
What do you say?
What's the next lesson? Like,
yeah, not sure.
Because if it just dives in deeper, then I think I agree. We should like build something in the next one, and then the one after
maybe
that.
If it moves on nicely.
Yeah.
So I think let's see what lesson 5 is about. Just so we know, chapter 5 is pet breeds.
Oh, okay.
The thing that we did already, but probably okay. That's interesting. I guess we could compare it.
Way past this. Are you guys doing the second pass now?
We just did the pet breed classifier without knowing that this is gonna come up. So it's essentially another example from we didn't scroll down. We were just like, let's build a pet breed classifier.
Oh, you guys on your own just decided to build a pet breed classifier.
Yeah.
Oh, that's hilarious.
And it worked.
And it worked.
Pretty well. Yeah.
That's amazing.
I wonder whether they're using the same. No, they're using different. I mean, who knows? Maybe it's the Stanford data set actually.
Yeah, we like Google data sets and.
Wow, good for you guys.
It wasn't even something that we were like, I don't know, like what should we do? And then we just Googled, what was it? Just like labeled data sets for machine learning. And then we got like a bunch of messy ones, and then we saw messy but also large, and we're like, all right, we're not going to be able to fit training something like this on this stream and it actually makes sense. So we found the Stanford dog breed one,
breeds,
and it was like a good size. So we're like, all right, fine, let's just do this one. now
Yeah, I think this is so it looks like it keeps rolling with bears. So
what if we just do this one next
fun.
And then apply, because this looks like it's doing way more with like the different data augmentation, and then just apply it to what we already built, and then
to the dog breed classifier,
and then compare the results.
Yeah, that sounds fun. That sounds like a good.
I mean,
it sounds like a good project.
It classified my dog, what we thought his breed was anyway, flawlessly out of like the 7 photos that we sent it. So, which is funny because we were like, I thought because he's like a mix. I think he's a Chesapeake Bay Retriever mostly, a Lab, and then a Pit Bull, and those were the 3 that came up with like the appropriate percentages. So maybe I'll just take a bunch of photos of him and see.
That's great.
What the differences are. Yeah.
Okay, awesome. I like that. So we're gonna do lesson 5 next time, but apply it on our dog breed classifier. Just like rework it. That gives us some reapplying and mixing.
Yeah.
Yeah. Cool.
All right. Cool.
All right. Very welcome to join if you want, because it's maybe a bit more interesting for you actually using fast.
The whole thing is interesting for me. I mean, it's good practice for me to teach always.
Sweet.
But it's just forcing myself to get exposed to it is good. So this is, otherwise I wouldn't. So otherwise I would just be watching TV or asleep or whatever. So it's good. It's a good use of my time. I appreciate it.
Yeah, same.
All right, cool.
All right,
So,
cool.
Okay, guys.
Yeah.
I'm gonna drop. Take
right.
care.
Thanks again, Gilad.
All right.
Yeah,
Bye.
of course. Thank you.
Okay,
Bye.
Bye. And I guess we'll just end the stream here. See you guys
Sweet.
on Friday.
All right.
Thursday.